for cleaner and healthier energy that the world wants. KHNP is growing with the world. A global energy company, Korea Hydro and Nuclear Power. KHNP is South Korea's largest energy company. From the first to the greatest and the best. The early challenges KHNP took on were the first steps forward to producing better energy and have now become great steps in the history of energy production. KHNP is a global energy company. A company replete with solid corporate assets, an excellent talent pool, and global recognition. By distributing advanced technology to various points around the world in need of electricity, from power plant construction to operation solutions, KHNP is positioned to become the world's leading energy company. KHNP is the leader of the future energy industry, enriching life with eco-friendly energy. KHNP continuously invests in new and renewable energy and R&D. By achieving technological innovations through integration with the Fourth Industrial Revolution, expanding its overseas business and new energy business, KHNP is preparing for a new future. A total energy company that grows bigger through change and innovation. A company that constantly challenges itself for a better tomorrow. KHNP is leading the global energy industry. A trusted global energy leader, Korea Hydro and Nuclear Power.
So, good morning, ladies and gentlemen. It looks like you, or some of you, enjoyed yesterday's evening very well, and they're not here. So, anyway, we have to continue. We have a new panel in front of us. Mr. Burkett excused himself. He was supposed to be a part of the panel, but he had to travel, and he handed over moderation of this panel to Mr. Krzywski. Another hiccup in the beginning of this panel is that we don't have Mrs. Kalivorova from Research Center Rzesz, so we're going to start with a second presentation, and we will see. Hopefully she'll join us later on in the panel, and we'll just change the sequence of the presentations. So, good morning, ladies and gentlemen. My name is Leoš Krzywski. I have been working in the Rzesz Research Center for 3 years, specifically in the section of hot chambers, where we're testing materials before and after radiation. And we're testing also various alloys of titanium, zirconium, and other alloys. So why are we researching these alloys? Well, it's primarily for the design of the 4th generation reactors that will differ from the current generation of reactors. One element that will be different is the coolant. We can use, for example, sodium, lead, bismuth or various gases with high temperatures, then melted salts and supercritical water as agents for cooling. But the problem is that all these agents are highly aggressive and they cause damage and corrosion. These materials will have to work under high operating temperatures, which again damages mechanical features. And also the reactors will use highly enriched material, which leads to making the material more fragile. So that's why we're developing and testing new materials. So just to give you an example, these are 4 potential reactors of generation 4. So I'm listing operating conditions, cooling media, and risks. All of the risks are related to corrosion. Helium is not such a big deal, but high pressure and corrosion. Well, high pressure causes corrosion and fragility. Supercritical water causes stress corrosion cracking. When the material cracks under pressure, for example, the reactor vessel has that problem, and molten salt reactors again cause corrosion.
Je mě slyšet lépe? Výborně.
So all of those conditions that I have listed determine the new conditions for the construction materials, resistance against corrosion, against high temperatures, against aggressive media, and at the same time they have to be able to work with radiation, resistant towards high radiation. So we have new alloys of titanium, zirconium, high entropy alloys, and I will explain that later on. The new reactor metals with aluminium, for example, and then nickel, super alloys, and SiC materials as composite materials. These are 2 charts. On the left-hand side, you can see the neutron cross-section and tensile strengths, and Young modules tensile strengths on the right-hand side. So basically, it gives us a probability that the neutron will react with the core of the atom. And mechanical features, I guess I don't have to explain that. The higher, the better. And you can see that the zirconium alloys have a good neutron capture, microscopic neutron capture cross-section. Then we also have titanium alloys and nickel super alloys that seem to be promising. High entropy alloys, what does that mean? For example, crystal lattice on the left upper side. That can be an alloy of a metal with a regular structure, regular grid, and the allocation of energy is regular as well with local minimal values. High entropy alloys can, for example, have 4, 5, 6 different elements with different potentials, with different atom radius, and they're structured in a pseudo lattice. It has a high entropy, that's why we call that high entropy alloys, and it's dynamically non-stable, and under certain conditions it would like to return to the stable and regular crystal lattice. And what is that good for? If we have an alloy which is radiated, subjected to radiation with neutrons, it causes damage. There may be vacancies or dislocations which decreased mechanical features. If that happens in a crystal lattice of an iron, for example, you cannot do anything with it because the material would degrade. On the other hand, if you have high entropy alloy with a non-regular or irregular allocation of atoms, it can partly compensate the damage. So radiating that alloy with neutrons may cause compensation of the damage in the structure and return to thermodynamic balance. So you can see an example of 4 high entropy alloys on the right hand side. So as you can see, there can be quite a few elements included, and it's based on simulated models. So what alloys can be used for applications? For example, IMI 834 titanium alloy with aluminium, zirconium, and SN. Modified alloys of zirconium with 12% of niobium or 15% of niobium, or 6 SN or 4 NB. The alloys that we use at this present for fuel usually uses just 1% of NB, so the increase to 12 to 15 is quite significant. And some examples of high entropy alloys. So on one hand, it looks like high entropy alloys could be the solution, but there are limitations as well. First of all, price, because they work with very expensive elements such as hafnium, neopen, hafnium, and tantal. Also, processing procedures are quite costly, and the samples that we test are often produced through additive technologies or sintration or annealing. And also it can become a problematic radioactive waste in the future. In research, together with the Math and Physical faculty of the University of Charles University, we have a project that is called Thatcher MKM, and we're preparing a project for additive technology used for the production of alloys. We do corrosive tests of corrosion with PWR, and we're able to do tests also with helium, and we also do tensile strength and cyclical damage tests and microstructure analysis. On the left-hand side, you can see the cross-section of the alloy with lead, and on the right-hand side, PVR autoclave exposure with corrosion layers and non-corroded layers. This is one of the high entropy alloys. You can see the cross-section after oxidation caused by lead. And on the right-hand side, you can see what happens when you expose it to helium with 800 degrees Celsius. Helium is not clean. So after 8 hours, the surface was this beautifully polished, and you can see individual particles of the material. So that's all from my side. Do we have any questions?
Well,
dear colleague, I remember a lot, and I have seen this presentation a number of times already, and I've always had a question on Jana Kalvorova or others in relation to slide 3. If you can switch to slide 3. This one? Yes. So as for Alfred and lead and risks of using this for cooling, corrosion and fragility or becoming fragile, that is, of course, that is a risk, but you have to know in what shape the lead is, or whether it's combined with something like bismuth, because the most important process that is happening is that the alloy elements are ripped out from the alloy. And that's probably the biggest problem that experts have been dealing with for the past 40 years. We saw it 40 years ago in the Russian nuclear submarines. And even though I have mentioned this at least 8 times in the past, I keep seeing this slide. Maybe you're young, you will remember my comment. So when we're supposed to use CO2 for cooling, what temperatures can you use so that it does not decompose to oxygen and CO, and then the free oxygen will cause problems? Well, I cannot really tell you, honestly speaking. I selected that just as one example, but I'm not working with this alloy. Those alloys that I work with are primarily with lead and supercritical water and melted salts. And one more comment. As for Allegro, you're talking about operating conditions of 580 degrees of Celsius and helium as a cooling medium. Why helium when CO2 would be enough? Because if you use helium, you have to get up to 850 degrees Celsius. And excuse me, but if you were my student, you wouldn't be able to defend your thesis in front of me. More questions, please? Well, if not, I would give the floor to our next speaker, Pavlo Rubielo.
Yes. Do you want me to start now?
Just a moment, we can see your presentation. Yeah, we see you now.
Do you want me to share my presentation? Just 1 second.
Can you, yes.
Cool. Should be okay now.
Yes, everything is clear now.
Okay, sorry for that. Should I start now?
Yeah, you can start.
Okay, thank you. So thank you very much for the opportunity of presenting this work about multiphysics. My name is Pablo Rubiolo. I'm professor at Grenoble IMP in France, and this work is being developed in CNRS. So I will talk about multiphysics modeling for nuclear systems, and I will provide at the end an example of application based on nuclear space on a nuclear space reactor. I will start the presentation just defining what is a multiphysics model, then give you some introduction to the model, the numerical model that we are using here, and then presenting some results for a microreactor for a space application. So let me start first with what is a multiphysics model and why we use that. So as you all are aware, there has been an evolution of on the nuclear reactor design from generation 1 to the current generation 3, and then the next generation 4 that should come later on. So this evolution on the reactor design can be linked to also an evolution or progression on the modeling, the numerical modeling capabilities. During the 50s, the industry used to work with semi-empirical correlations and experiments in order to design the nuclear reactors. And as the computer power increased, we moved to models that were 0D, 1D, 3D. By year 2000, we start seeing coupling between standalone codes like neutronics and thermohydraulics. These days, we are working with what we call multiphysics codes, and these tools are very important for the development of the next generation of reactors, but also for the current generation, because they let implement approach like best estimates plus uncertainties, VPU, which actually let improve the design of, for example, the nuclear fuel. So what is a multiphysics model? Multiphysics model is a numerical model that actually will solve a set of couple equations. These equations are usually written from first principles, and they will they'll include the mass, momentum, and energy conservation that probably you know, also the neutron transport equation, and sometimes nuclear and also chemical reactions. So as I say, the equations are developed from first principle. That means that we should not make that many assumptions in developing the model, and the equations could be solved more or less coupled, or more or less could be numerically integrated more or less simultaneously. So it depends actually on the way we implement the algorithm. These multiphysics tools usually provide very high fidelity results that concern the space scale, but also the time scales. And they are well suited to implement best estimates approach. Now, what are the advantages and drawbacks of multiphysics models? Well, the advantage are, as I already mentioned, is that they can let us implement best estimate approach, and determine best estimate values, doing also propagation of uncertainties. They let us access to time and space scale that were not possible with the previous model, and they allow us to study the coupling between individual phenomena. Now, they also have some drawbacks and challenge because they are quite complex. So first, if the multiphysics model is to be able to develop a multiphysics model that represents the reality, we must be sure that we're including all the relevant phenomena. That means that usually we need to develop first a paired phenomena identification ranking table to be sure that we are not forgetting something. They require high computing resource, and that could be a problem. Sometimes that will preclude actually the utilization of the multiphysics model. They need to be fed with a lot of a huge amount of input data. Sometimes it's not available. They may have problems during the integration, the numerical integration. And if we want to use them for safety studies, then we need to develop or adapt at least the current safety methodology. So there are also licensing issues if you want to use this for nuclear reactor design and safety studies. So an example of a multiphysics code is the Vera platform that has been developed by the CASL consortium in the US. So this is one of the most complete multiphysics platform available that can be used for PWR, and I think also for VWR, and that use the operative splitting strategy, meaning that you can see on the figure there, you have different codes that actually will exchange information between them, and each of these codes are developed independently from the other one. So the use of Vera for safety study poses some challenge because of the licensing issues that I mentioned before. So why CNRS is working in this multi-physics approach? What is our motivation? Well, motivation is related to the scientific challenge that we have there. So first, there are challenges concerning numerical aspects. So how we will do this? This is, for instance, a field where we can use surrogate models like artificial neural networks or reduced order methods. We are also interested in challenges related to phenomena modeling and the coupling between those phenomena, and I will show that more in the case of the space reactor. This is also interesting if you want to develop new nuclear system designs, because in theory it could allow reducing the number of experiments that you may need to do. And also is another area where there are important challenges is for nuclear safety methods, so which is also a very important topic. So let me give you an overview now on the multi-physics program here in Grenoble, and in particular what we are doing between the modeling effort and also the experimental part. So the goal of our multi-physics program is to develop numerical models and the related multi-physics experiments when it's possible for advanced nuclear systems, in particular for those systems where there is a strong coupling between the phenomena. What is not an objective is to develop a multi-physics platform like Vera, because this is beyond our capacities and also our objectives. The starting point for our activities was the studies that we initiated on the molten salt fast reactor, in particular on the Salmon Safer project. It was an European project that started around 2015. So the strategy that we develop in our program is to work usually in a small nuclear system where there is a strong coupling, and then apply this developing the numerical tool for the modeling of those particular systems. When it's possible, we develop also experiments that can be used to validate the numerical tool. So in the presentation, I will show you the example of the space reactor, but we have worked also in other topics like criticality accidents or the molten salt fast reactor. So the multi-physics model, I will just explain very briefly, but there is a lot of information in my slides, but I will just give you an overview of this. Our multi-physics tool, it is based basically in a couple between Serpent, which is a Monte Carlo code, and OpenFOAM, which is I would say, a C++ toolbox for developing different numerical solvers based on finite volume method. So OpenFOAM, we use it in practice for doing CFD, computational fluid dynamics, and then solving part of the equation of the system. So in our multi-physics model, we have three main, I would say, modules or domains. One is the neutronics, where, as I say, we will use Serpent in general. Then we have the thermohydraulic part, so basically the CFD part, where we solve the Ram's equation, and then we may use a thermomechanic model that can solve different phenomena like solidification or melting or thermal expansion. Sorry, my computer is frozen. Can you hear me?
Yes, we can hear.
Yeah, I'm sorry. well, I will go ahead, but I cannot move. I will, okay, now it's fine. Sorry for that. I don't know what happened. So let me just go briefly on this. The neutronics model have basically two type of methods. One that is Monte Carlo, as I say earlier, with Serpent, that for cinetic calculation will use a quasi-static methodology. It means that it will calculate the shape of the neutron flux with the Monte Carlo code, and then it will, over a very short time step, will use the equations that are equivalent to the point kinetics, but not exactly that. It's a very accurate method that works very well with very small systems. Otherwise, we can use a transport method that is the SPN method that could be SP1 or SP2. For thermal hydraulics, as I say earlier, we will solve the Ram's equation. So these are the Reynolds average Navier-Stokes equations, and for that we will use all the libraries that are available in OpenFOAM. So the idea there is to solve the conservation of the mass, the conservation of the impulsion, and also of the energy. We can solve different type of phenomena like conduction, convection, thermal radiation, and also conjugate heat, so exchange between a fluid and a wall, for instance. The thermomechanic part is used in generally when we are working with materials, pure materials like a molten salt, where you can have solidification and melting. So for that, there are two models, one that allows solving the solidification melting process at the macro scale, and another one that is called Musophone that actually let us solving the solidification melting process at the scale of the crystal. So this is a very detailed thing. Otherwise, we can also use this model to study problems like thermal expansion and behavior of a structure. To finish this, I would say this very short presentation on the multiphysics model, let me just talk about the experiment. So, as I said before, we have a platform here in Grenoble. The name is FEST. So this is a fluid experiment and simulations in temperature. Basically, there we are doing thermohydraulics and thermomechanics. And the idea would be that once we develop a model, we will identify by a PERT, we will identify which are the main phenomena, and we will try to develop experiments in the platform to validate the accuracy of the numerical models. We cannot validate everything there, like for instance, neutronics. We don't do that. For neutronics, we will use like other benchmarks that could be available in the literature. So let me talk now on the case of application. So a microreactor for a space application. This is a project that started 3 years ago. The idea is that in the coming years, we think that nuclear fission may play a significant role in a space exploration. There are different types of fission reactor for space propulsion. We are looking at nuclear electric propulsion. So basically, the reactor will produce thermal power that we will use to obtain electricity for an electric propulsion system. So for this particular type of reactor, we focus on a molten salt reactor because we think that there were some intrinsic advantage on this type of reactor for the particular application of space propulsion. So in particular, in a molten salt reactor, we can, in theory, work at very high power densities and temperatures. We have a system that usually operates at low pressure and can have very low temperature gradients. This is very important for reliability, in particular for a reactor that is used for space applications. And also, the other advantage is that a molten salt reactor can have very simple reactivity control system. So these three things make us think that it could be a good idea to look at this type of reactor for a space application. Of course, there are problems, there are issues with material, with neutron damage, with the power conversion system, with the testing that would need such system before it can be deployed, and also the phenomena that are very, very coupled. But so the idea was to use the numerical tool we have to study this particular system. So let me just give 2 words about the design process, because the design process for this reactor is very different for a reactor that is used for electricity production on Earth. For an space propulsion reactor, what you want is to have the lower mass as possible. So you want to reach criticality with the lower mass, and you want to have a reactor design that has very high reliability. There is no maintenance. So the feature that is very important is the reliability of the systems. And also, as you can imagine, safety studies are very different from the one that you would do for a power production reactor. So the starting point of the design process is the determination of the minimum reactor mass once you have set up the layout, more or less, and the material that you want to use. So even for a molten salt reactor, which is relatively simple, there are many options that you have for the material. So the first step in our work was to select the materials. And for that, we perform a large number of simple design calculations where we use different materials. For instance, for the molten salt, we investigate 8 different fuel salts. For the reflector material, we look at 7 types, moderator the same, and for cladding material, 3 different types. So for each of these, each of the different combination of those materials, we calculate the critical mass, and from that we came with a couple of designs that look for us the more promising. One was a fast reactor, and a fast reactor design. The other one was a thermal spectrum reactor. Here I will show in results only for the fast spectrum reactor. Now, for a space application, it is important that the current policies are that we should not work with high enriched uranium. So we performed the study for 2 different fuels, a high enriched uranium as a reference, I would say, and then but we focus the main effort in a low enriched uranium, so meaning that the fuel has about 20% of uranium-235 enrichment. So in the slide that you see now, I am presenting the geometry, the approximate geometry of the reactor. It is very different from what we used to see in general. You have the core cavity that is an sphere that is void. There you will fill up with the molten fuel. The molten fuel will enter through the pipes that you can see above, and it will so it will heat up inside the cavity because of the fission reaction, and then it will just go out for another 6 pipes, outlet pipes that are also in the upper part of the cavity. The pumps, the heat exchanger, and the shielding, it is outside I would say the core. There is a reflector that is also has a spherical shape. It's a spherical shell that is around the core cavity. So, and between the core cavity and the reflector, we have a cladding, okay? And between the cladding and the reflector, we also have a thermal insulation to lower the temperature in the reflector. So for the molten salt, and after the preliminary design study where we look at different materials, we finally select LEF UF molten salt, which is a fluoride, and is more or less well-known molten salt. We found that this provide the best, or among the best results, globally speaking. And then for the fuel, as I say, we use 2 levels of fuel enrichment. The one I presented here is the low enriched uranium fuel. The high enriched uranium was used as a benchmark actually to see what was the difference if we were able to go to much higher uranium-235 enrichment. So the power level we set at 1 megawatt, and the reason was that we want to get the maximum power for a given size and for the critical mass that we obtain. And that level was set up according to the material limits. And for the cladding, we select an titanium, zirconium, molybdenum alloy, TCM, which has shown in the past to have good corrosion resistance up to 1,100 degrees Celsius. So reflector, we use beryllium because it gives the best performance. And the table on the right is showing you the main parameters, and in particular the dimension of the reactor. So here, just to show a few results that we obtained from the multiphysics model. Obviously, if you want to do this, calculate this system, you cannot use a standard codes, because here you have the fuel that is molten and then is flowing inside the cavity. So the fuel is entering through the inlet pipes. There are 6 here. I'm showing only 2. And you can see on the left, on the figure on the left, you can see the velocity field, the magnitude. You can see the jets that are formed by the pipes that are going inside the cavity. On the right side, you can see the outlet pipes, only 2 of them. And basically, what we see here is that there is a very good, there is a well mixing in the cavity. So the fuel is well mixing, which is a good thing, because then we can imagine that the radiation of the fuel is going to be homogeneous. So if you want to solve this system, you will need to use Ram's equation for sure. So in the next slide, here we are seeing the flux, the neutron flux. On the left, you can see the thermal flux. On the right, you can see the fast flux. So this is a fast reactor. There is no moderator inside the cavity. So you have the fast flux that has a peak in the center, more or less in the center of the cavity. And the thermal spectrum has a peak inside the reflector, which is beryllium. And what we obtained from this simulation was, what we conclude was that the fluence on the beryllium was below or about the limit that we set up to avoid significant swelling on the material. You can see also that the upper part, because of the inlet and outlet pipes, there is more leaks, neutron leaks, and the thermal flux is a little bit lower than on other sides. In the next slide, we are presenting on the left the fuel salt power density, and then on the right the temperatures. So the power density, what you can see is that there is an increase near the cladding. The reason is that there you have thermal neutrons that are coming back from the reflector, and therefore that is causing an increase of fission rate due to thermal neutrons. Inside the cavity, the power profile is more or less flat. And you can see also in the inlet pipes, there is a little increase on the power there. The reason again is the presence of beryllium that is surrounding those pipes, and then you have a peak of also of thermal flux on that. Nevertheless, when you look at the temperature field, you can see that the fact that you are working with a molten fuel, so a fluid fuel, liquid fuel, means that actually this peak of temperature near the cladding have not significant effect on the temperatures. So the temperature profile is more or less flat inside the cavity, which is good. We have very small, actually, the temperature, the maximum temperature difference is below 50 degrees inside the fuel. And the other thing that you can see is that the reflector is working at a much lower temperature than the cavity. The reason of that is the thermal insulation that we have between the two of them. For the calculations, we were considering that there is part of the energy that is directly released on the reflector. So this is because of gamma heating and also neutrons. And then we will also considering that the reflector will radiate it to the space. So there is thermal radiation on the surface of the reflector. So taking into account these things, we obtain temperature fields that are quite acceptable with respect to the requirement that we set up. So this is an example of a calculation using the multiphysics model, and as you can see, I mean, trying to model this system with standard codes would be very, very challenging. So the tool that we have put in place, it is able to tackle such a particular system. So let me finish my presentation just with a couple of comments. One is that the multiphysics approach are getting more and more applications both in the industry and in academia. There are applications not just for energy, nuclear energy system, but also for other systems. We have also been working in application for nuclear medicine. This approach are very important for the design of advanced system, but also for nuclear power plants, existing nuclear power plants, and also to study like new type of nuclear fuel like the ATF. But having said that, you have to keep in mind that the multiphysics approach is not always the more efficient approach. So this is requires a lot of input data. It can be very demanding from computational point of view. So it's not necessarily the best tool in all situations. So, and my last comment is on the needs for more stronger international collaboration. There is an initiative from the EIA that is the ONCORE project, open source nuclear code for reactor analysis, that is actually promoting the use of open source multiphysics simulation tools, and that is looking for other participants in this initiative. So with this, I finish my presentation. Sorry for the break in the middle, but when we do this from far, sometimes some things do not work. Thank you.
Thank you for your presentation. Máme nějaké dotazy z publika?
Thank you. Any questions from the audience? Nobody?
We have no questions.
No questions? Okay.
Thank you, Mr. Professor. We have a reward for every presenter. It's a small present for the bees living on the roof of our faculty, so we will give you the present as soon as we can. And now I will give the floor to Antonín Rudolf, our next presenter from Škoda JS. Good morning. My name is Antonín Rudolf, and I work for Škoda Nuclear Industry as the head of engineering, machine engineering, and I specialize in virtual reality and 3D scanning. When I was preparing this presentation, I remember a moment when I remembered some information about virtual reality, that it's not suitable for aircraft industry or nuclear industry, but it's no longer true. I would like to show you some projects in the Czech Republic and also partly in Slovakia. When I read articles about extended reality and virtual reality, you save a lot of money and it's very effective. That's what they say, but I don't understand how they do it, how they calculate this. First, let's look at augmented and virtual reality conditions that we need. After that, we will look at the utilization of VR and AR in Škoda. And after that, we will look at the utilization in Temelín and Dukovany. In order to use virtual reality or augmented reality, first you need data so that you can create and optimize a model. You can, for instance, scan data. You need to reduce the number of polygons so that you can optimize the model and so that we don't need a huge server. After that, we create a virtual environment. It needs to be tailor-made. We need to get rid of all unnecessary aspects which bring more costs. And then the work itself in the virtual environment. For instance, when we have it, we train everybody, all members of the team. During nuclear days, you could see the Škoda JS exhibition. You can see a lot of our products we made. Some of them you won't be able to see anymore because they will be sent to our customers. For instance, if you want to see the reactor vessel or inner parts of upper and different tools, you can see them at the exhibition. And the use for Temelín power plants, we designed SIPs. This device was made with utilization of VR. For the assembly, we made a presentation to the customer, one-to-one example, and we also discuss implementing VR for partial assembly. This is a video of a colleague from the assembly who started to use VR. You can see in the video other colleagues who were present there, people who were in charge of the assembly. So our colleague could see it in VR before he started to assemble it. He could get ready for all complex operations and tasks. This is the latest use of VR. We combined preparation for welders, for the metal bellows weld for Temelín. There was a mock-up tool, but at the time the metal bellows weld wasn't available, so thanks to VR they could test it and check it. We also use VR for modeling. You can see the video here. This was a design of wire route. Modeling wires and cables is quite complex. You have to meet all instructions of the customer thoroughly. So we use this construction and put it in a mock-up model. This is an application we're working on. It will be in the Dukovany power plant. It's the dispatch of the Škoda 440 container. We can prepare the training in virtual reality. It's the preparation of the container for loading, fuel loading, and then also the removal of the load and the drying of the fuel. Right now in Temelín, they already have one center for virtual reality. They have a test for containment. As you can see this model, it's very complex. There is a lot of pipe work. Each part has a certain number of polygons, and each polygon has specific requirements for computer capacity and power output. Right now, there are two routes or two test routes, and even visits can go to the parts of the plant which are not normally accessible for people without a given security certificate. In a study from 2021, we found out who could use VR most, and we established that it was the machine engineer operators. So we asked about their requirements and we used the requirements for this model. Here you can see one part of the containment tour. When I go to Dukovany or Temelín, I don't always have the opportunity to go everywhere, but thanks to VR, I think I know the containment pretty well. And I already know where everything is, more or less. Another advantage of VR is that you can reduce or adjust visibility, or also add, simulate fire for firefighters. This is for this year's project. Design and preparation for TQ and TX engines, transport route for these engines in case of defect. I don't know the exact time needed for the transport. In this, VR is an additional aspect. It's mostly about identification of collisions. We updated the model in PDMS. We used scanner for that. And the most important part is the design of the transport route. Throughout the project, we also made this video. And as you can see, the assembly team will be able to see and watch different videos and see the engine moving. And with the engine moving, they will see different collision boxes and they will be able to be very well prepared. They can stop, turn the presentation, the animation, and they can see everything they need. This is a transport of engine for the TQ pump. This is one of the easiest routes. Here you can see the large opening. If you know Temelín power plant, you know that there is a wall which will need to be torn down. It will be a big challenge. In one unit, there are 9 TQ engines that need to be transported and 3 TX engines which are easier to transport. And this is one of parts that you could have already seen. There was the repair of the steam generator in ETE EDU. And as I already said, I also work with scanning and 3D prints. Our team continues to use scanning and they are always really careful about bringing me back the scanner. This is the result of the scan of feed water. As you can see, the heterogeneous weld, which was replaced. Our Slovak colleagues also prepared a 3D mock-up, which was less expensive than using a metal version. To conclude, even though as Škoda JS we supply plant parts, currently, because of legislation, we're not allowed to supply parts using 3D print. So this is a call to our regulators. We've already made progress, and we are trying to advance in this area, and I hope we will catch up with our foreign colleagues. Thank you for your attention.
Thank you for your presentation. Do we have questions? Michal Pánik from Atom. I suppose that you use technical documentation as input data for your models. Is that right? Well, it's a mixture. When we were doing the transportation of engines, we didn't have the real situational data. So we used a scanner and modeled it and handed the database over to our customer. And when you talk about steam generators, we had a project design documentation, which was delivered to us together with the product, with the machine, but we used the scanner to make it more precise. One more question. Well, since you're able to do this using the 3D scanners, would it be possible to solve a post-emergency situation, for example, post-disaster situation? You would be able to scan, for example, temperatures of surfaces and so forth. Well, I have not shown this to you, but we also use a software, and we participated in developing that software. And thanks to HoloLens, we're able to send a robot to the given location, and the robot is using HoloLens and for scanning that location. So what happens is that we can send data back to the HoloLens, and the user would know on the given location what needs to be done. And the HoloLens can be used to scan all sorts of parameters such as radiation data, temperature, and so forth. And we're able to simulate and send all the data necessary. It's not a problem. Safety is a problem in the core area or inside the VDR 1000. You don't have any signal, of course, because there's a thick layer of concrete that's blocking it. But we managed to solve it somehow. Chess allowed us to use, or made it possible for us to use Wi-Fi inside the containment. So I think that if we came with that requirement, it would be possible to do it. And we also use an offline regime that's been tested already. For the questions? Do we have any experience with people, with future users that will use this virtual reality on their work site? How much do they remember? For example, if they use the virtual reality and the space simulated in VR, and then they have to work in the real environment, they may seem like, well, I have seen this, I have touched this. People have different levels and quality of memory. So I guess you will have to sort people to those that will remember it from the VR and those that will get the real knowledge only when they touch it in reality and work with it in reality. Well, I know what you mean. You're right. Virtual reality is not suitable for everybody. People may get sick, or if somebody doesn't even have a computer at home, and then you equip them with virtual reality, they're not able to work with it. But we have feedback from people that tested virtual reality in the steam generator, and people confirmed to me that it was really identical, that it's one-to-one model. So there's no distortion. The only difference is that unless you want to make huge investments in virtual reality, you will not be able to feel the mass and weight of the given parts that you're handling. And also when we tested VR in the containment, we got positive feedback, because then in the real environment, people were saying, oh yes, I do remember this, I saw that. So I tested it, and from my own experience, I know that when I looked at a specific location in virtual reality and then I went to that location, I, for example, remember the route, I knew where to go. Okay, thank you. Mr. Stanislav Lenhardt is the next presenter.
Se zeptám, jestli můžu podívat na to. Ještě do toho mluví trošku líp, než tady to. Dobrý den. Dobrý den všem.
So, good morning to all of you. First of all, thanks to all of those that have organized this conference. It has become a tradition, and I hope it will be a long tradition. And I'm glad I can have a presentation on the qualification of new and developed advanced types of fuels for light water reactors. I'll do an introduction, and then talk about activities of our company in material research. Then I'll talk about a program concerning nuclear fuel. I'll talk about materials and methods, and then I'll do a summary. And if I should present specific outcomes to you, then I would need the whole morning, and that might not be enough. So the combination of pellets of UO2 and fuel from zirconium alloys, that's what we use as the basic fuel element, and it's the basic and proven concept of fuel cells for most reactors, PWRs, BBRs, and so forth. Zirconium has been used in nuclear energy since the 70s of the previous century. There are major positives of that material. High temperature of melting, low effective through-cut, and also good mechanical and corrosion resistance. Zirconium and alloys of zirconium stabilize the other elements in the alloy stabilize or provide stability for zirconium. We use zirconium NB alloys, E110, 125, M5, and modifications, and we have multi-component alloys, E635, Zircaloy, and Zirlo. Why do we need the fuel coverage program? We have such a program at a number of plants, and it's a traditional instrument to monitor the life cycle of the reactor vessel. And that program also monitors the radiation aging of various concrete elements of the primary circuit and other parts of the reactor. We use that program in reactors from 3 to 6 years, and there's a regular replacement program. The burnt out fuel is then stored for 10 years in a wet environment, in wet pools, and then it is transported for dry reposition in repositories where it can be for 40 plus years, easily 100 years and more. So of course we have to know the features of the stored burnt out fuel at the end of usage and at the beginning of repository. We have to maintain integrity and the ability to handle the material. ATF is what we're paying attention to a lot in reaction to Fukushima Daiichi disaster. There are experimental layers placed over the burnt out fuel. We use experimental data to measure the neutron flows. Of course, to survey and analyze radiated material can be quite costly and time demanding. Corrosion is the biggest problem in nuclear fuel, and I'm using an example of PWR, BWR, and VVER reactors in this table. Zirconium alloy reacts with water, and you can have positive and negative outcomes of that. ZiO, that's the positive outcome, and hydrogen, that's the negative outcome, because it disrupts the material quality of the fuel. When we monitor corrosion, we basically study a non-active material. It's a part of the program. We do it in an autoclave in various environments. And the difference from active tests is that we don't have any active neutrons. And also during the campaign, the concentration of the BO acid is changing, while in the active environment, that would be stable. We look at the kinetics, the corrosion, hydrogen concentration. We do mechanical tests and the analysis of metals, metallography. Josef Gotch last year talked about this, so I'll just tell you what is new. We have two projects for the International Agency for Nuclear Energy. We have two projects focusing on the development of this fuel from these alloys with a coating based on chromium. These materials would be suitable for VVER and PWR. We also have another project for a cutting device of a new generation to cut the radiated samples of a new generation. Let me mention two more projects, MCA and Ampule V&V chess. We have radiated clusters with samples of zirconium alloys that are researched in Rzesz and other sites. And apart from segments of zirconium samples, we look at the development of various features of the coating. MCA is a material cluster which uses the same component as the head of the cluster. We have bearing bars and ampules below it, or capsules below it, with zirconium alloys. So there are two capsules with the samples and one sample capsule in between that monitors the fluency during radiation. The segments of zirconium alloys are E110, 125, and 635, and their modifications. These are the parameters of these samples, and these clusters are located in the active zone of Unit 1 of Temelin and PP, and we try to locate them in a position with a maximum flow of neutrons, but it must not be located below the cluster. The samples of zirconium alloys differ in terms of heat processing. We have three types: full recrystallization and cold rolling. So this is the time schedule of the two projects. They're interconnected. 2012 MCA projects, and 2014. That's when the fuel material was transported to the first unit of Temelin. We already finished radiation. We cut off 4 clusters out of the 6. Next year, we're planning to cut off the 2 remaining clusters, and the project should finish roughly around 2025. As I said, we have 6 material clusters. So 6 values of the neutron fluency. We have 5 radiation cycles. So it's not a mistake on the slide. After first 3 cycles, we managed to achieve a relatively high level of fluency, and we agreed that the last 3 will not be located in a location with maximum flow of neutrons, but will modify it. So we have 5 radiation cycles rather than 6. Then the cutoff of the material capsules, that's what you see here. It's in the transport container, and the cutoff is done mechanically. Without any remote interference. The cutoff is done in that way that the device brings the material cluster into POMA, POMA, and then weights are lifted, and we cut off the material cluster. The capsules are then transported into a container and transported to a research center for analysis. So this is an example of the material cluster and one of the capsules that's being taken out. The material analysis should determine the limits for a safe and reliable operation and manipulation or handling with the fuel. We analyzed non-radiated samples of the material to test proof methodologies. The analysis on the radiated samples is used to describe material features and to map its development, and also to compare it with a non-radiated material to see how the features develop in comparison with the reference sample. We will use the outcomes in various mathematical models for gradual implementation for advanced types of fuels. So this is the overview of the analysis in projects MCA and VNV. Various types of analysis on the left-hand side, TM, SEM analysis, mechanical tests of neutron fluency, hydrogen volume, fatigue tests, reorientation, hydrates, and so forth. So when you have a bigger capsule with the various alloy segments, when you take the capsule out, then the real capsule may look like a fuel bar.
This is the scheme for analysis. There are different microscopes with, for instance, microscopes with reflected neutrons, mechanical tests, tensile tests, tensile properties, fractography, microhardness, nanoindentation. To sum it up, the fuel coverage keeps developing. Right now, it is focused on the development of ATF. Our program is interesting because of the predictiveness of the material during irradiation, and it is important to compare the irradiated material with the non-irradiated material. The MCA project is important because the alloys are irradiated in real-life conditions of a reactor. And in both projects, we are interested in development of methodology, analysis of irradiated materials, and also monitoring the development of material properties. We want to continue with these activities. We are already about to start the MCA2 project, and in 2024 we would like to have amended and updated samples, especially ATF samples we made during the projects I mentioned, and we would like to incorporate them in Temelin in 2024. Allow me to thank our partners without whom we wouldn't be able to achieve all of this. Thanks to UJV, to ČEZ, to Škoda. In collaboration with Škoda, we also work on an updated POMA, which will enable us to cut several material clusters at one time. So that will save us a lot of time. Thank you for your attention. Thank you for your presentation. Are there any questions? Could you please go to the third or fourth slide with the advantages and disadvantages of the zirconia coverage? I agree with all of this, but I'd like to see more disadvantages. For instance, one lesson we learned in Fukushima is that the reaction of hydrogen, zirconia, and steam, the reaction of hydrogen and ZrO2. For some time, people were thinking about going back to using steel, but it would not be that advantageous. The thing is that hydrogen is a huge reminder in these severe accidents. And some people also complain about zirconium from this point of view. And another big disadvantage that we can, however, accept is that zirconium alloy has twice as worse a lambda than the other. So usually difference of 20 degrees. It's a huge gradient. We know all of this though. So you presented a wonderful preview of activities for your future, where you research zirconium alloys with E110, but Czech and Slovak will not have Russian fuel. It will be mostly Westinghouse or Framatome or other fuels. But your research is focused on Russian alloys. So is there any potential correlation, or are you going to adjust your program? We opted for Russian materials because the MCA project is taking place in collaboration with a Russian research institution. We are using 110 because the clusters and the capsules are made of 110, and that's why the project studies this material. And it's an advantage because we have a real-life material used in a reactor and it is already irradiated. That's why we opted for this. But for the other coupons, there are other materials similar to the, let's say, Western materials. So there is a certain correlation to some degree. And there is one more question. I probably have a stupid question, so sorry about that. Is there a place in the fuel rod capsule where in the fuel capsule, is there place for the capsule or yes, that's a very good question. The material clusters are inserted in the pipes instead of old clusters. So you have 312 rods, and a traditional cluster has 18 rods, 18 capsules, and ours only has one inner circle. So you don't need to modify the set, you don't need to modify the cluster, because it does not affect in any way the characteristics and properties of the active zone, and the fuel rod remains as it is. If there are no other questions, I would like to thank our colleague and give him our present from our bees that live on the roof of our faculty. It's funny that honey and the VVER fuel have one thing in common, and that's the hexagonal form. Thank you very much. And now, Vladislav Benir and his presentation.
Já začnu i bez prezentace. Jo, jasně.
I will start without, there it is. So this is my presentation. Every time I'm about to make a presentation, I always try to come up with something new and original, as we manufacture interesting and original things. So I used an old title of a presentation, but with a new topic. First, I would like to introduce myself. I'm the guarantor of the nuclear machine engineering. The biggest news you could have heard is that Škoda is no longer Russian. We are now under ČEZ. I think that's good news. It will open us, it will open the way back to the world. In my presentation, I'd like to look back in the past first. We were part of construction of several nuclear plants recently. So I would like to present a few facts related to the new builds. This is a reactor hall where we make the largest machines and devices, and these are then later transported to NPPs all over Europe. Right now, this is, I think, the 23rd container body of Škoda 1000. You could see it if you came to our plant. And the first container also for Dukovany was made 440, and we also already exported the last OS caster for 40. That was the last one of this line. This is one of the first interesting things we made. In 2006 and 2007, we constructed a support frame for OL3. After we manufactured it and sent it to OL, this is a frame for the reactor vessel. Here you can see it being assembled and put in place, put in the right position. And the interesting thing about this is that the nuclear power plant is only being commissioned this year. So we made this support frame in 2006 and 2007. Then we also made a barrel. This is the core barrel. The manufacture started in 2005. And now in 2022, the NP has just been commissioned. I think it was commissioned in January. And this is present day. We are currently working on inner parts for an English NP. You could see it now being worked on in our factory. There are two bodies, two parts, and it's a unique project because, as you can see, we manipulate it like this, vertically, under the welding machine. And when you see all the sizes and all the size of the welds, the height, so the welders are almost like climbers because we are making a product that is has the most strict requirements in terms of quality. This is a view from the top. You can see the welding of the same part from the top. Another part, this, let's not talk only about welding. Thermal processing is also interesting, and that's what we do. For instance, thermal processing of a weld of the core barrel, which will soon be exported to Hinkley Point. We are still talking about the Hinkley Point NPP. This is a site of ours where we have a record number of annealing sources, of annealing tools, 14 of them. Here, as you can see, this is the annealing zone. It's 400 degrees, is the stabilization annealing point. Each part of the zone has to be handled and dealt with carefully. Recently, we ordered this service, but right now we are doing it ourselves. We have specialists that can design it and calculate it, and this is the result of our annealing activities.
So this is just a picture of the annealing machinery, all the cabling. So that's an image of the assembly of core barrel into a vertical position that makes it possible for us to do welding. There's a special setup of welds that I'll show to you later on. That's for those that haven't heard any of my presentations before. This is TN3/1 work site, and that's where the history of welding of our pressure vessels was written. We were welding the 1000 and 440 vessels in the past in this hall, and there was a few years break when we did not manufacture so many products, so we used the time to upgrade the work site, and now we're welding this core barrel for EPR. This is a unique device. There's this head which is being welded at this time. It has a thickness of 550 millimeters, and we use that head to weld casings which are 465 millimeters thick. It's a thin gap weld, and we have half a degree on each side, a minimum gap, if you can imagine, half a degree. Basically, the weld gap does not open at all, and we're able to move the welding head in that gap. So this is the core barrel weld, and of course this austenite material behaves differently than that black carbon material. So the austenite is different, the color is different. So this is when we started the first weld, and when we look at it later, we have to do a visual inspection, and this is what the weld looks like. So that's what our predecessors developed when we were welding 440s and 1000 sets. And we weld the material in 3 stages, and you could see on the previous pictures how we weld it in a vertical position. We have a locking position of the 2 parts, and we have a temporary weld that is then machined. And then after welding it with the temporary weld, we move it to a horizontal position, and we weld it automatically with a melting agent, and then we machine process it, and we cut off the core, which is most risky when it comes to flaws, and then we cover it with a permanent weld. So we haven't found any defects when we apply such a process. So there's a high chance of having a 100% reliability with an X-ray check. So this is how we weld the elements for Framatome. And when we were assembling the first core barrel, we had to justify this method in France, and we were successful, so we can use that method still, even at present. This is the first core barrel that will be located in Hinkley Point. You can see it here on the carousel, so it's its full size, and it's stainless steel coating that you put inside the pressure vessel of the reactor. So on this slide, you can see the location in England, where it's going to be, and just a few photos of preparing the construction site so that we can bring in our components and assemble them. The start of that construction was in 2018. It should be completed in 2027. So another nuclear component that we produced was a transportation element for Flamanville. So this is the carriage that will be then used in the corridor. So we used this trolley to transport the material in the corridors. So this is just a delivery that we used in the reactor, the transportation trolley. Flamanville started in 2007 and allegedly it should be commissioned in 2023, and our transportation trolley will be used there. So I wanted to tell you about one project that does not relate to nuclear power so much. We were putting together a ammonia reactor for Slovakia, and we're welding steel of 15,421.G, which is difficult to weld. So I'm going to show you what we did with the final welding. So when you're welding the reactor, it's rotating, but those components that heat up the welded point to 250 to 325 degrees, they have to be static. So while this element rotates, that silver element, the isolated part, must remain static. So we have a special process of staging it into preheating segments, and we have a special structure for that, and ball bearings to allow the rotation of those segments. So these are special structures or fixtures that we use to heat up those specific locations for welding to that high temperature. We're annealing with temperatures of 650 degrees, which is quite a lot to maintain that stable for processing, for controlled processing. So that's again the ammonia reactor R201, and annealing the final closing weld, because the reactor was so big that we could not fit it in our furnace, which is 15 meters deep, and we had to do the annealing outside. So when you do the annealing, you don't really see much because it's all insulated. So the only chance to see the composition of the annealing elements, you have to take a picture before starting the process of annealing. So that's this picture. And as I said, it does not relate to nuclear power, but if possible, we're also active in chemical production, chemical sector. So that's the ammonia reactor being transported to Litvinov. So now I can show you a few pictures of our training center in Pilsen. In ARC Heating, which is a company that cooperates with us on various projects, we have a training center And in that training center, we train our own staff as well, because in line with nuclear legislation, even the welding staff, the welders must have certain official qualification, otherwise we would not be competitive on the nuclear market. So we have trained operators and other trained staff for heat processing. And this is a picture from the training center. So I am a member of the jury together with my colleague, and we're training the welders and other staff for heat processing. I don't know whether you have this mock-up device here at an exhibition. Yes, this model. This model is exhibited here. Sura ordered us to make this. And it's a model of deep repository of bent out nuclear fuel. It's just a part of it, actually, because that repository is so long, that so huge, that we would not be able to make a proper model. I have a few ideas for next time for presentation. For example, laser with added material. We also generate our own nitrogen for the lasers. So that will be for next time. And Mr. Jan Carlos, that you can see on this picture, celebrated his 90th birthday, and we invited him to come to our company. We presented some products and technologies to him and gave him a present or a few presents for his birthday. And some of the academics were there too. For example, Mr. Zdebor, who is here with us today. So this is just an interesting fact that I think we should not forget to mention. So this is us, that's our team. That is my team for special welding processes and heat processing, and nobody else will praise us. We have to praise ourselves. So I'm virtually patting my colleagues on their shoulders. And that's it. That's the last slide. Thank you. Thank you. Do we have any questions? Well, I'll praise you too. I can acknowledge you as the Czech guarantor for welding. You work for Framatome, French company, Hinkley Point, OL3. Well, the French guys, and we heard it yesterday, they have a big problem with welding. And because of the wells, the 32 of the decommissioned units out of 56 had to be decommissioned for various reasons, but mainly for welding. You have training centers, robots, automation. Why don't you help them? Well, that's a question, difficult to answer. We do help them. We help them at present, but I'm not so much aware of their historical development. But to give you the context, they wanted to prevent problems with welding, so they check us a lot, they inspect us a lot. We don't have even 1 millimeter of leeway. We have to work according to their instructions, and we have to solve our problems first, and we don't have time to solve their problems when it comes to cleanliness or sticking to instructions. There are always at least 3 inspectors sitting at our back and checking on us. So Well, why don't you turn it around? Well, you know, that's a political question. They have a slightly different position because they are the ones that pay. Okay. Any more interesting questions?
Takže ozaj pre mňa toto bola asi, prepáčte ostatní, ale najkrajšia prezentácia.
Well, that was probably the best presentation for me. I'm from a company dealing in decommissioning of nuclear components, and you presented the behavior of components after many years, that basically they do not degrade. And to manufacture these large components, containers, to put them together, lock them and weld them, it's not easy. Precision is very important. So what's your competition globally? As for containers, and I'll focus on Europe, we won over a German company, GNS. You could see their last castor that we manufactured for them, but that's made of cast steel, and we won because we used a higher quality structure of steel. Technologically, it was a must. We had to weld it together. But when it comes to the quality of the material, of the whole component, of that casing, well, you know, on one hand, we work for them, but in this tender, we won. It is one of the largest companies in this sector in Europe. Of course, in Japan, there are other companies in Korea, in China, in Russia, in the United States. There are offers coming from all over the world, from companies that Mr. Zdebor mentioned. So when it comes to manufacturing containers, there are competitors that we have to compete with, but we're succeeding in tenders. So Škoda is successful, and we also try to have it under control on the Czech market, at least. And we win thanks to quality, I think. I'm a technologist. I don't really deal so much with the financials, with the price. I can tell you about quality. So do we have any more technological questions? If not, thank you for your attention. Thank you. And thanks to all the other speakers. And just like the others, you will receive a bottle of honey from our beehives that we maintain on the roof of this building. Thank you. And thank you for moderating this panel. Unfortunately, we haven't heard one presentation because our colleague, Mrs. Kalivodova, simply has not come for some reason. So we can afford to have a longer break. So you're all invited to a coffee break, and at 11:30 we will start with the next panel.
cleaner and healthier energy that the world wants. KHNP is growing with the world. A global energy company, Korea Hydro and Nuclear Power. KHNP is South Korea's largest energy company. From the first to the greatest and the best. The early challenges KHNP took on were the first steps forward to producing better energy and have now become great steps in the history of energy production. KHNP is a global energy company. A company replete with solid corporate assets, an excellent talent pool, and global recognition. By distributing advanced technology to various points around the world in need of electricity, from power plant construction to operation solutions, KHNP is positioned to become the world's leading energy company. KHNP is the leader of the future energy industry, enriching life with eco-friendly energy. KHNP continuously invests in new and renewable energy and R&D. By achieving technological innovations through integration with the Fourth Industrial Revolution, expanding its overseas business and new energy business, KHNP is preparing for a new future. A total energy company that grows bigger through change and innovation. A company that constantly challenges itself for a better tomorrow. KHNP is leading the global energy industry. A trusted global energy leader. Korea Hydro and Nuclear Power.
Společnost UJV Řeš navazuje na více než 6 desítek let zkušeností svého předchůdce, Ústavu jaderného výzkumu. Společnost dnes prezentují špičkoví odborníci, technicko-inženýrské a projektové služby, aplikovaný výzkum a unikátní technologická infrastruktura. To vše ve službách bezpečné a spolehlivé energetiky, průmyslu a nukleární medicíny. K dnešní klientele z celého světa patří hlavně provozovatelé energetických celků, státní dozorové orgány, investoři náročných průmyslových technologií, původci radioaktivních odpadů a pracoviště nukleární medicíny. Jedním ze stěžejních úkolů ÚJV Řeš je podpora bezpečnosti a spolehlivosti jaderných elektráren v České republice i ve světě. Z legislativního hlediska jde hlavně o průkazy jaderné bezpečnosti zařízení, z provozního pohledu je to škála aktivit zaměřených na sledování, kontroly a vyhodnocování provozních parametrů, jejichž výsledkem jsou návrhy konkrétních opatření pro zvýšení bezpečnosti a spolehlivosti provozů. V oblasti palivového cyklu se specialisté z Řeše soustřeďují na podporu licencování paliva pro reaktory a jeho efektivní využití. Zvýšení efektivity paliva v provozu bloků řeší ÚJV Řeš zejména vývojem nástrojů pro optimalizaci palivových vsázek a programů pro monitorování aktivní zóny. Řízení životnosti jaderné elektrárny představuje propracovaný systém péče o složité technologie různých typů. ÚJV Řeš se touto oblastí zabývá i na mezinárodní úrovni, zpracovává programy pro řízené stárnutí konkrétních komponent, je autorem řady certifikovaných programů a metodik. Základnu pro řízení životního cyklu tvoří zkoušky mechanických a strukturních vlastností materiálů, hodnocení jejich degradace v náročných podmínkách, svědečné programy tlakové nádoby reaktorů nebo kvalifikované inspekční metody a postupy. Podporu provozovatelům zastřešují komplexní projekty řízení životnosti a zvyšování výkonu průmyslových celků. Akreditované laboratoře společnosti působí v oblastech pokrývajících vybrané vlastnosti materiálů, akreditovaná zkušební měření, zkoušky a analýzy.
Jsme Doosan Škoda Power. Už více než 100 let vyrábíme špičková energetická zařízení. Jsme světovým dodavatelem systémů turbogenerátorů, komponentů a služeb v oblasti projektování a výroby. Využíváme nejmodernější technologie a neustále do nich investujeme. Patříme ke spolehlivým zaměstnavatelům. Významně podporujeme vzdělávání a rozvoj našich zaměstnanců. Rozsvítili jsme miliardu domácností po celém světě. Jsme Doosan Škoda Power. Roztáčíme svět kolem nás.
Since the beginning of the 1980s, we at Fortum and the VTT Technical Research Center of Finland have been developing APROS, a comprehensive, accurate and user-friendly software product for modeling and dynamic simulation of power plant processes. Using only one code, you can simulate operations of the entire power plant or specific isolated processes for a variety of engineering and training purposes. One code comes with many benefits: savings in purchasing computer codes, model design and maintenance. It increases the accuracy of the simulations, as there is no need to handle the integration of different codes between different models. High accuracy is also ensured by reliable solvers, extensive models and component libraries validated by nuclear industry standards. When planning a new or upgrading an existing plant, APROS helps you test different design solutions, find optimal control and process equipment parameters, and even test the real INC cabinets before their installation. The model, developed for engineering purposes, can be used for building a training simulator, saving money and time. Models are built utilizing an easy-to-use graphical user interface, and model parameters can be changed during simulation. Programming skills are not required. It's enough that the model developer knows the processes which are modeled, and if necessary, APROS can be easily integrated with other codes. We at Fortum want to share our knowledge. For further information regarding APROS, please contact us.
Vydavatelství Publishing představuje svůj hlavní titul. Časopis Průmyslové spektrum, nejčtenější strojírenský časopis, který přináší aktuální informace o domácích i světových trendech v jednotlivých odvětvích oboru. Časopis je určen pro střední a vyšší management, konstruktéry, technology, pracovníky výzkumu, vývoje i pro učitele a studenty vysokých a středních odborných škol. V jednotlivých vydáních měsíčníku Průmyslové spektrum se náš silný tým zkušených odborných redaktorů zaměřuje na průmyslové obory, které jsou v České republice silné a mají potenciál růstu a reflektují změny v ekonomice a v různých oborech podnikání. Hlavní pozornost je věnována výrobní technice a technologiím, které jsou nositeli inovačního pokroku a zrcadlí se v nich výzkumně vývojové milníky nedávného období. Velký důraz je kladen na kvalitní a zajímavý redakční obsah a edukační dosah. Přinášíme reportáže z výrobních podniků, vedeme hovory s osobnostmi českého průmyslu, tlumočíme názory odborníků z výrobní i akademické sféry. Věříme, že tímto náš časopis přispívá k osvětě strojírenských oborů a k jejich popularizaci mezi širokou veřejností. Vydavatelství Publishing, to jsou inovace v průmyslu, strojírenství a výzkumu pod jednou střechou.
Ladies and gentlemen, we continue with the next section. I would like to introduce Mr. Vondrovits from SURAO. And as always, there's a slight change in the program, so we will start with the first presentation, and you're not going to miss out on anything. I'm giving the floor to Mr. Herbeck now. Good afternoon. Welcome to the next section. We are going to discuss the future, or what the future will look like when nuclear plants are decommissioned. So what happens to the spent fuel, to radioactive waste, and we're experts on this topic. Let me invite Mr. Herbeck from Rzesz, who's going to talk about research in nuclear plant accidents. Thank you. Ladies and gentlemen, my name is Jan Herbeck, and I'm the head of a group working on experimental research in nuclear power plant accidents. So we look at nuclear power plants and what happens when something undesirable happens. But it's an important topic if we want to increase the safety of nuclear power plant reactors. I have prepared a brief presentation. First, I will talk about cold crucible induction melting. We use this technology in our experimental activities. I'm going to talk about the construction solution, its utilization, and the behavior of a melt during a temperature above 2000 degrees. There is a wide potential for utilization of this technology. I picked only a few examples for the purpose of these nuclear days, and I picked one specific topic, the interaction of core with different materials. Core is what is the result of the active zone melt during a nuclear power plant accident. I have an example. First, the interaction of core with the material of elliptically perforated bottom of the supporting cylinder of VVER 1000, and also the reaction with the thermal shielding of VVER 1000, and also with innovative anorganic materials. On the left side of the slide, you see the induction furnace with the cold crucible. There is electrical current inside, which leads to magnetic field. And because of the magnetic field, there are joule losses, and the melt. Part 5 is the wall of the crucible. You can see other parts, 1, 2, 6, and 7. What is the difference between a traditional cold furnace and the cold crucible? The cold crucible is intensely cooled by water, so its walls are relatively cold, and there is a slight layer in a solid state material, and this isolates the melt from the crucible and the crucible from the material, so there are no impurities getting inside the melt, and thus we can reach quite high temperatures, and we can also melt very pure materials. This configuration is used for oxide melting. We use it for simulation of nuclear accidents. We prepare this with the help of a powder, and we examine and monitor different phenomena. On the right side, you can see the view of our working chamber. Number 1 is a meter for contactless temperature measurement. This is the only possible approach under the temperatures we use. We could use about 3000 degrees, which is not a technology limit, but the limit is the temperature measurement. So it doesn't make sense to use higher temperatures if we can't measure them. And it's not feasible with contactless measurement. Number 2 is a normal camera, which shows the level of the melt. Then we have another camera, number 3, which shows different states of the melted material as it is within a vessel. And also the operator is protected during this experiment, of course. Number 4 is a protection against aerosol. Number 5 are different sensors we use to describe the system. And number 6 is the cold crucible. It is on a special positioning device. And with this device, we can change the position of the crucible towards, in relation to the rest of the device. When we prepare an active experiment, we prepare a mix of oxides that represent core in the form of a powder. And we use either natural uranium or low-rich uranium. We don't use a natural fuel, and the isotope structure does not have an important effect. This is a skull layer. I included 4 pictures. It's a melt of ZrO2. Before the experiment, we added another oxide of chromium, So the layer on the bottom is no longer that narrow. You can see the differences in the thickness. That is the skull layer. How can we use this technology? We use it to model severe nuclear accidents, either to study crystallization mechanisms or to provide to research phase charts, to study material properties and to study material interactions under high temperatures. And this last part can be done in two ways. We either use a sample of a material and we put it in a core, or we can spill core on the material. You can see an example of that in the picture on the right side. When we spill corium, we can simulate only the first few seconds of the entire process. We can't simulate the residual heat. So it's only the simulation of the first impact. We can also use the technology for synthesis of materials in a liquid stage under high temperatures, for glass melting, and also for crystal growth. These are just a few examples of possible applications. There are many of them, and these few examples show what we do. This is behavior of a melt of ZrO2 and other oxides. It's a 50-50 ratio at 2000 degrees. And in a moment, you will see how the mixing happens under 2400 degrees. You can see the intensity of the mixing at this temperature, so it's faster with higher temperature. And if we continue to increase the temperature, the speed will increase as well. I selected 3 specific examples of studies of interactions of corium with other materials. We measured properties of corium and analysis of its spill at high temperatures. This is a project we have together with UJV. First is the interaction of corium with the material of an elliptically perforated bottom of a supporting cylinder, then interaction with the thermal shielding in the reactor, then density and corium viscosity measuring, and also the corium spill calculations, as well as the impact on the bentonite melt, on the concrete melt. We are using real-life conditions from Czech power plants. Our colleagues from UJV used the Aztec code to calculate 2 potential accident scenarios. For first scenario was a station blackout and then large blackout. They got all the necessary parameters, temperatures of core at the moment of the accident, and further on, we decided to use the station blackout scenario, and we conducted experiments that I'm going to describe later. This is the sample for the core interaction with materials in case of perforated bottom. That is the sample of the perforated material. It was the same bottom that exists in Temelín. Of course, it's just a model. We can't use a 101 model, so it's a reduced size model. We put it in a vessel where we usually put the core during such moments, and we studied whether the sample will melt and whether it will leak through the holes in the sample. This is a video of the core being spilled on the sample. You can see the vessel where corium is leaking. On the bottom of it is the sample, and after the experiment, we conducted all analyses. You can see all the aerosols. And the results. We already showed before, 2 slides before, that the temperature was supposed to be at least 2200 degrees, and our measured temperature was 2028 degrees, and that's because of the aerosols. We measure it optically. We need to see the object that is being measured and the amount of aerosol. That is why the temperature needs to be recalculated because of that, of the aerosols. And that's why we calculate the real value, and that's 2240 degrees. So we met this condition of the experiment, and the height from which we spilled the core was 200 millimeters. And that was, again, we met all the necessary requirements.
It was interesting that we had more than 3 kilograms of core caught on or stuck on the sample, and more than 700 grams under the sample. And this is the sample after the experiment. On the very left-hand side, you can see the solid core after the experiment, and after eliminating the core, you can see that there was no major melting going on. We also conducted chemical analysis, and you can see that the color is light green. That's due to the chemical aerosols from the spill below the sample. So our colleagues from SUV modified their code in MELCore, and they extended the time for catching the core on the sample, and we were able to delay the interaction of the core on the material, so it corresponded more with real life. The second part was dealing with the shielding of the floor of a VVR 1000. The objective was to find out whether the core will melt through the floor. And you can see the model on the left-hand side. We have sheet metal, a few layers of sheet metal with air layers in between, and a thick metal sheet as a cover on the outside. You can see the sample already manufactured on the right-hand side. You can see a vertical cross-section. We did it because we were afraid that if we fill it with the core of more than 2200 degrees temperature, that the pressure will be too high. So we allocated some thermal sensors on it, and you can see in the video the melted core being poured on the sample. We're spilling a little bit outside of the vessel, but that happens. So in this example, just as in the previous, the measured temperature was lower than the calculated. We were pouring the core from the height of 203 millimeters, which did not exactly correspond with the model, but it was within an accepted deviation. And there was a little bit less than 1.5 kilos of the spilled core on the sample. Over 2 kilos of the sample were outside, leaking outside. And you can see the core being caught on the thermal shielding layer. And this is the cross section of the sample. Those shiny bits, that's the metal, because the core melted the lamellas and created metal islands. And all of the core was caught on the sample. Lamellas were deformed, but the shielding survived without any major damage. There was no melt through. So our colleagues from UJV included these outcomes in the simulation in melt spread and core quench that deal with cooling of the core during accidents, and also the ablation of material and behavior of the core during an accident. We do not focus only on existing power plants, but also we focus on new materials. So we take part in a project called New Unorganic Materials for Nuclear Industry. Our colleagues are designing and testing innovative sacrificial materials and special powder fillers and immobilized aluminum silica geopolymer matrices. So I don't have to give you all the details of the materials, but they have a patent on that. So there's an article also describing in detail what materials they are developing. We tested those innovative materials, and in this video you can see a mixture of core with sacrificial material designed by our colleagues being spilled on a heat-resistant surface. And that material of the surface is basically being tested, because that should be used as the outer layer, a heat-resistant layer. And we wanted to know what would happen when we mix the core with the sacrificial material. This is the photo after the experiment, and you can see a cylinder. The cylinder is a heat-resistant material, and on the top you have the mixture of the core and the sacrificial material, and the slab remained as it was. Nothing happened to it during the experiment. So that specific material looks promising. One more interaction that we did on the project, but not as part of that experiment that I showed to you in that video. This is an analysis of the core with the sacrificial material that our colleagues designed. And you can see on the left-hand side an image from an electron microscope, electron image. And you can see uranium in the middle and gadolinium on the right-hand side. You can see that there's a homogeneous distribution of gadolinium, but in the bottom right of those images, of those three images, look quite similar in uranium, in gadolinium. So that would make that material quite promising, because gadolinium has a large cross-section for neutron catching. So as a sacrificial material, that could be used for preventing reoccurrence of critical states in the reactor. So to sum it up, I talked about induction in induction melting in cold crucible and what it can be used for. All those experiments that I have described when we use melted core and its interaction with materials, I have to highlight that we're able to analyze only a few seconds of that experiment, the first few seconds. We cannot do very long experiments. I also described our studies of interaction of the melted core with various materials as part of different projects. So that's all on my side. If you have questions, I'll be happy to answer, or you can contact me later on. We can have a discussion. Thank you for a very interesting presentation. Do we have questions? Well, I have 3 questions, I guess. Well, first of all, interaction of the core with the sacrificial material and so forth was already analyzed by those that designed the core catchers. So how did you compare your results with the results of the work done by large companies, those that designed core catches, Russian companies and others? So that's my first question, the comparison of the outcomes. Second question, how did you manage the thermal balance of the whole experiment? So you first calculated the thermal shares in the simulation, I guess. And what did you do next? And the third question, what is the material of that pressure vessel that the core should melt through? Okay, as for the first question, it is very difficult to get outcomes of those analyses from those companies that you're mentioning, those that tested it in the past. But I didn't say that we have quite a long cooperation with our colleagues in Japan, thanks to the accident in Fukushima. And we tested their sacrificial material for them. So we have our own experience with that material. It's difficult to reach outcomes of other measurements, and also the core catches are slightly different. The Russian ones and the French ones, they differ. So it's difficult to make general conclusions. You can compare your outcomes with the individual core catches, but the purpose of the core catches of different manufacturers is also different. As for the pressure vessel, originally we wanted to analyze the melted core interaction with the pressure vessel material, but we didn't get the material of the pressure vessel. But you have it in Rzesz, don't you? Well, I contacted colleagues working on that experiment, and they told me they don't have any pressure vessel material left. And if I find out the source, they wanted to know the contact as well. Well, you can try Škoda. Well, then we modified the experiments, and we had that perforated bottom, but that's a stainless steel material of the bottom of the shaft of the reactor. Is that right? Well, yes, the perforated bottom. Yes, that's it. And we had a problem with terminology as well, because they used different terminology in Dukovany and Temelin. So for VVER 1000, we used terminology used for 440. As for the shielding of the floor, the core also had some iron oxides So that's what probably would get into the core from the structural materials in case of default, in case of meltdown. So we made that mixture. And as for the thermal ratios of the experiment and comparison with reality, well, our colleagues from UJV did that. They conducted a dimensional analysis. Okay, that's enough for me to know that they did it. They conducted that. Okay. Well, thank you for the questions and answers. Do we have any more questions? If not, thank you, Mr. Herbeck. And we can move to the next presentation. And of course, we will also receive honey produced by our bees. And we also have one present for the head of the panel, head of the section. Well, yeah, but I have to deserve it by completing this section, this panel. So I'll move to the left of this room because I noticed that you're watching this screen rather than the other one. So in my presentation, I would like to show to you the status of the preparation of the deep repository in the Czech Republic and in other countries as well. I'm a geologist originally, so I apologize that maybe it will be too rocky, too surface-like, but the rocks, different types of rocks, are the foundation of what we walk on Earth, and we also have to look at it when we plan the deep repository. So, as for the environment suitable for deep repository, there are three different environments that are considered around the world. First of all, clays. Clays that are fantastic for sedimentary rock, and it's fantastic for storing, because if you store something in various types of clays, the only way for migration is diffusion. So, for example, French colleagues or Swiss or in Belgium, they use that environment for repositories. We can also use crystalline rocks, more solid rocks, which are excellent for operating safety, because if you build a tunnel or any opening, that tunnel will remain stable and solid for further 200 or 300 years. It does not change its structure, just like in clays, for example. But of course, there might be cracks and water might leak through those cracks, so you have to do a lot of modeling for that. But the first examples of that kind of deep repository show promising results, for example, in Finland. And in the Czech Republic, we believe that our deep repository will also be in such an environment in the future. The third type of rock or rocky environment used for the repositories is a simple salt. As a sedimentary rock, salt is excellent because it's a homogeneous rock. It encloses itself. The water does not complicate things, and it's a very stable barrier. So a deep repository in salts has already been functioning in the United States in 150 meters depth in New Mexico, where they have deep repository for trans-uranium and other radioactive waste from the American military program. Then also Germany. Germany is testing out salty environments for repositories, as well as the other environments. So we'll tell you about that later on.
What is the situation in the Czech Republic in terms of radioactive waste management? We have an administration, the SURAO. It was founded in 1997. And according to them, we have sufficient capacity for storage of all current and all possible future radioactive waste. Right now, we have low and medium level radioactive waste. We have 3 sites. One is in Litoměřice, Richard, that's for medium level waste. Then another one is in Bratrství near Jáchymov. And our largest one is in Dukovany for low radiation level waste from the operation of both NPs. We are developing the deep repository right now, and we are trying to find the final and the backup location site for the repository. The repository should come in operation in half of the century. It will have 2 parts. The first part is the above surface area. There will be, the radioactive waste will be accepted there. Then there will be special chambers where it will be repacked, and then through special infrastructure, it will be stored underground. The site will have 2 types of storage space. The first and the largest one is the space for spent fuel from nuclear power plants, and the smaller storage site, as you can see here in the picture, is the repository for all other types of radioactive waste, which cannot be stored anywhere else in any other storage sites or repositories. And a large volume of the stored material will be waste from decommissioned NPPs. The area of the site will be of 2 or 3 square kilometers. It will be deep as 2 kilometers underground, and it will meet all necessary legislation and nuclear regulations. It will be able to store up to 9,500 tons of nuclear waste. It will have several extra reserve for the size of 3 Temelín nuclear power plants for 60 years of storage. And the repository will be used only for material that cannot be stored in other repositories, other types of repositories. Our concept is quite simple and sophisticated. It's a system of interconnected barriers. The largest barrier is the steel container. You heard about it in the previous section, so I don't think we need to talk about the details of the container, but its main function is to stop radionuclides for as long as they are dangerous. This container will be put in special holes, boreholes, and it will have a special sealing. The sealing also slows down the flow of radionuclides and also prevents corrosion of the material. And if there was any leakage, it should ensure diffusion. And now the environment itself, where the container will be situated, it's a very, very stable environment, which should also slow down the flow of radionuclides into the biosphere. This is the case of the largest part of the repository, but we will also have a similar system for other types of radioactive waste. The only exception is that containment doesn't have such a big safety function. There will be concrete containers in the other cases, and the containment of radionuclides will be ensured by a fixation matrix. There will be huge caverns, which will be filled either with concrete or clay again, and that's where the radioactive waste will be stored. And now the schedule of the opening of the repository. It started back in the 1990s, before the creation of SURAO. So we are the second generation now that is working on the opening of the repository. And in 2030, we should choose the final and the backup location site. After that, we should complete the selection of devices and barriers. In 2035 up to 2040, we will ask for all the necessary permits, such as the construction permit and the licensing. And by 2050, from 2050 to 2065, we will ask for a permit for a trial operation, and then we would like to see the official operation to start in 2065. In July this year, the European Parliament voted and approved the conditions of taxonomy, its rules for funding and of the nuclear energy and other rules of nuclear energy use. If a country wants to meet these conditions, a deep repository is one of them. And it should be put in operation by 2050. So if we want to accept this condition as the Czech Republic, it will definitely affect the preparations of the deep repository. In terms of searching for the location site, this has been going on from the very beginning of the process. In the 1990s, there were about 32 sites. In 2003, we opted for the solid rocks, so there were 6 sites. In 2011, we added more location sites because the public was not happy with some of them. And in 2015, we narrowed the selection. And that was an important turning point. It was very important because, all in all, we thoroughly described all location sites. We always looked at all criteria, and we managed to list all differences of the location sites. We have 3 groups of them. Group 1 is Březový potok, Horka, Hrádek Janoch. Group 2, but Group 1. Now, in terms of the criteria, when we were comparing location sites, there were 13 of them, and we put that on a paper, and we specified these based on 39 indicators. The criteria included long-term safety, environment impact, operation questions, etc. What's next? It will be given by the policy of radioactive waste management and also of our strategy that changes every 5 years. We update it every 5 years. We would like to complete it in 2024 and prepare an assessment of the current storage system with the double steel container. And then this concept will be compared to the geological conditions, and then we will see which criteria will be met and which location will be the best. Compared to the rest of the world, I think we're doing quite well. I have also prepared a few slides about other countries. Let's look at Germany, our neighbors. Germany announced a huge phase out of nuclear energy. They are now implementing a program of BGE, which is a state agency. It's a repository for spent fuel only, and the rest of the radioactive waste will be in the center of Germany, in the Konrad repository. Germans consider all types of rocks, whether it's salt or clays or crystalline rocks. And in 2013, they restarted the program entirely. In 2020, they announced they have 90 location sites. They are about to narrow the selection now. But after they narrow the selection, there will be a surface testing and a surface research or examination, phase 1 and phase 2 and phase 3. And we're currently exchanging information with them and cooperate with them a lot. Another comparable country in terms of deep repository is Canada. We have also rich cooperation with them because they opted for crystalline rocks and also sedimentary rocks. It will be an inventory of 25 CANDU reactors. That's a different fuel than the one we use, but the system is very similar. The difference is that their container will probably have a copper finishing. Canadians restarted their location site selection program. It has become voluntary, it's on a voluntary basis. In 2015, in 2010, they had 27 sites, in 2015, 22 sites, and in 2022 sites. Next year, they would like to announce the final allocation, but because of COVID, it will be postponed. They would like to start with the construction in 2033. Switzerland has had a huge success because on Monday, a press conference of Nagra, a repository company, took place. Nagra managed to find the safest final repository location. It will be in clay layers near the German border. So there will also be a cross-border cooperation with Germany. They will store all types of radioactive waste. low-level as well as high-level radioactive waste in one place. So their repository will be a lot like ours. And what I like about their concept is a trial or test repository. As you can see, first they use this test repository with first containers, or let's say disposal packages. And if it's technically feasible, then they will continue and store in a regular system of disposal galleries.
So they should start the licensing process in 2024, then 2050. They should start with the operation for the low active spent waste and high active spent waste. Should be ready to be stored in a repository in 2065. We know that Switzerland is very developed and progressed when it comes to local democracy, but they will not hold a local referendum. They will have a national, probably a national referendum to decide whether that project should get a green light or not. Finland, that's another country for a deep repository, and they selected a site close to Olkiluoto nuclear power plant, and they built a trial facility there called Oikalo. The deep repository should be used for spent fuel from Loviisa and Olkiluoto NPPs. If there should be a need to store spent fuel from Hanisa, for example, they will try to find a second location for a deep repository. So this repository is mainly to store spent waste from NPPs, but a few years ago, Finland also extended the purpose of that repository to HLWs and ILWs kind of waste. So you can see the time schedule. The state decided in 1983 to build the repository. In 86, they had 5 locations, 92, 2 locations. And 2001, they selected the final location, which was approved by the parliament. And they asked for an operating license in 2021. So next year, they should start with trial tests. They will bring the first model disposal container and store it in the deep repository. So if Finland acquires operational license and proves that it is safe to store waste in such repositories, it will be a progress. It will be definitely a step forward in the EU when it comes to storing radioactive waste in deep repositories. Thank you. And if you have any questions, please ask. Well, probably you will not know this, but what is the elevation of the entry into the Swedish and Finnish repository? Because we keep hearing that will be flooded in the future by seawater. So if the repositories are too low, that could be interesting for the future. So what's the altitude? Well, I visited both of those sites. I don't remember the altitude. It will be up to 10 to maybe 20 meters above sea level. And the scenarios count on on a possibility to be flooded or to be below sea level, and the design should be resistant to seawater flooding. They use copper containers in Finland and Sweden, which should be resistant to corrosion. And if you taste the water in that depth of 400 meters, up to 400 meters, they're used to water having a high content of minerals. We don't have that problem in the Czech Republic. Okay, now the Czech and Moravian repositories. The agencies and authorities do not see any enthusiasm on the side of municipalities. So the municipalities are primarily afraid that they will lose supplies of underground water, and their wells will become dry due to the construction in the various depths of so when you construct the repository. Another drawback is that there will be huge excavation works that will have to be done. So try to travel to Chibram region, and you can see the huge piles of soil excavated. So I haven't heard or read anywhere what they plan to do with all these problems. First of all, the loss of water. So what happens when the water starts permeating into the shaft, and also what happens with the excavated soil. The operator of the repository omitted to provide that info to the municipalities. So they shouldn't be surprised that municipalities do not want to volunteer. Well, we try to explain, and we understand the concerns of various local communities. I myself visited a number of discussions and spoke to local people. So we've mentioned two things. First of all, the soil. The repository will consist of roughly 70 kilometers of tunnels, underground tunnels, but of course the 70 kilometers will not be there at the end. A part of the excavated soil will be used to fill in, to backfill the operating tunnels. When it comes to the huge pile of soil that will remain afterwards, of course we have various plans what to do with that soil, and we were also considering the overall landscape of the locations to be able to spread the soil across so that we don't have a pile of soil at the end. The municipalities have a say in the discussions. We offered to them that they can participate in local working groups, and in those working groups they can voice their concerns, and we can then reflect those concerns in our projects. It's a voluntary effort, voluntary working group. So some municipalities decided to send their representatives, others did not do it. So it's up to them. As for the impact on the water resources, that was one of the criterion, and we analyzed whether the repository can have an impact on water sources. It was a criterion K10, and we did not see any negative impact. If you have any question, you can come to us, to our agency operating the deep repositories, and we can have a discussion on that. If we don't have any more questions, then we will thank you. And now we'll give the floor to Mrs. Lahodova, and she will tell us what we do in the effort to manufacture the best steel container in the world. Good afternoon, ladies and gentlemen. I'll continue talking about what my colleague Mr. Ondrovits started. The topic of my presentation is a disposal container for spent fuel, spent nuclear fuel. But before I talk about the disposal container, I'll talk about the spent waste, the spent fuel, because then you will understand why we require to have a robust container that would last for 1 million years, for 1 million years. So we'll have two sections of the repository, one to store spent nuclear fuel, and in the second section we will have other institutional waste and waste related to decommissioning of NPPs. So can we go back? Yes. So on the right-hand side, on the top, you have an image, and I have it from CHESS, and it shows very well what I'm talking about. If you look at the volume of the radioactive waste, the NPP waste is only 1% of the volume. 90% of the activity is generated by the NPP spent fuel. So that's why it is very important to isolate that kind of fuel, because then we'll be able to very well isolate other radioactive waste from the outer environment. So on this chart, again, we're discussing burnt or spent nuclear fuel. We have time in years on the horizontal axis and radio toxicity on the vertical axis. So the horizontal axis, that relates to uranium, because that's what we use to manufacture fuel to nuclear waste, to nuclear plants. And you can see that fission products are most active, but they have a short half-time, so their activity in time goes quite strictly down. Yodium-129 causes a problem because its half-time is 16 million years. But then the plutonium isotopes also cause a problem because their radiotoxicity gets below the radiotoxicity of uranium in hundreds of thousands of years only. So that's why we talk about safety, and that's why we need to have a disposal container that will last for roughly hundreds of thousands of years. The criteria were set out by the Act on Radioactive Repositories. As for the engineering barriers, well, we're using a disposal container, and the engineering barrier is the bentonite, the form of the waste, and the container assembly. So our principle of developing the disposal container was a part of a project. That project lasted 9 years, and the main partner on that project was Škoda JS. The project was split into 4 stages. In the first stage, we conducted research, we described parameters and processes. In the second stage, we selected potential materials. So we conducted thermal, technical, and mechanical calculations. In the third stage afterwards, which we extended with a third plus stage, we focused on corrosion, because corrosion, that's the most important process that impacts the life cycle of the disposal container. And in the fourth stage of the project, we manufactured a sample of a disposal container used to verify the technology, but also it is now being used for presentation. Requirements on the disposal container are defined by a governmental decree, and there are also requirements of type D for disposal containers of type D that we have to fulfill. Of course, the container must isolate and keep the radioactive particles inside. It must provide for shielding. It must provide for the handling outflow of heat, and the whole system must be below critical, subcritical. So it must be physically impossible to create critical or above critical situations, conditions. Also, it must be feasible and technically manufacturable, and we must be able to handle that container. So the optimization threshold for radioactive dose is 0.25 millisieverts per year, and throughout the whole life cycle, that optimization threshold must not be exceeded. The life cycle of that container is 1 million years. The hydrostatic pressure, we have a conservative value of 20 megapascals. Another requirement relates to heat, because of course the spent fuel and radioactive waste generates heat, and our condition was set at a conservative level of 95 degrees. So in the deep repository, the temperature must not exceed 95 degrees. And we count with a temperature on the storing horizon being 25 degrees. Maybe when we have more details and data, the temperature might go down, but we expect to have this temperature.
In our disposal package, it's a double coat package. It has a steel container. There are two types of steel: carbon steel and also corrosion resistant steel. In the deep repository, in the future, the conditions will be different. There will be different temperature, there will be oxygen, and bentonite will not be homogeneous. So the retaining and isolating function could deteriorate because of corrosion, some local corrosion. And therefore, the isolation function will be ensured by the carbon steel, because it corrodes more quickly, but it's more stable and steady in terms of corrosion. It's easier to predict than in other types of steel. So it will be resistant to corrosion, and then this corrosion resistant steel will take over the isolation function and feature of the container. The carbon steel must be made under specific and strict conditions in terms of impurities content. These concentrations that you see were established or set in the third part of the process. And this is the package, disposal package. As you know, that in Dukovany and Temelín, there are two different fuel types. The upper package is from Dukovany. The diameter is the same for both. It's about almost 1 meter, but the upper one can have seven fuel capsules, while the one down is only for 3 fuel capsules. And that is also because the temaline fuel generates much more heat, and because of the heat we need to have only 3 fuel packages and no more, as the temperature could get too high. It has turned out recently that it will be hard to demonstrate the lifespan of the disposal package. So we have another alternative. We could use carbon steel, and it will be 2 separated parts so that we can respect the necessary gap. How many disposal packages will be stored? Under the official policy, the Czech Republic plans to have 3 more NPPs, and they will probably have the same operation as the Temelín nuclear power plant. So we will be able to count the fuel packages, the fuel capsules, and we think that the average number of years will be 60. And the disposal package for Temelín fuel contains 7 packages. That was for Dukovany. For Temelín, it's 3 fuel packages. So we can easily calculate how many we need to have in total, and the total number is 7,600 of such packages that need to enter the deep repository. You might have probably already seen this picture from my colleague. This is how we're going to handle the spent fuel. We think that we will be able to transport 3 wagons like this in one time. Corrosion experiments were the most important ones in the process. These pictures show how they happened. They took 3, 6, and 9 months so that we could see the evolution. The experiments took place under various temperatures for different types of bentonite. Some of the samples were irradiated under both aerobic and anaerobic conditions, and today we have a new corrosion program. It's taking place not only in our lab, but also in Bukov, and we're trying to simulate as much as possible real-life conditions that will exist in the deep repository on a 10-year horizon, because the situation changes. As you can see, the experiments were quite rich, and the assessment was also, because of that, quite difficult. It took place in the Czech University, VSCHT, and in Hřeš. The calculation of input power of the dose equivalent that determines if we can get close to the package or not. So we calculated the limit on the surface, on the disposal package, and also the calculations 2 meters in a 2-meter distance from the package. That is for the Dukovany fuel. We also made thermotechnical calculations, also because of thermal dilatation, and the construction and the design is not easy at all. We have to take into account the dilatation, and we need to take into account that the temperature in the repository will not exceed 95 degrees. We also made strength tests because there will be an outside pressure of 20 megapascal. All the containers, even the inner containers, need to be able to resist such pressure, all of them. And the highest pressure is in welds, as usual. So here you can see how we improved the network so that we could prove sufficient strength of the container. And now the lifespan of the disposal package. When we talk about technical devices that are made all in the same way and are then exposed to the same power or phenomena, they are distributed based or divided based on the Weibull repartition. As you can see, there is a very high peak, which is a disadvantage because it means that these packages can get damaged at a fast, very quickly, at a short moment. So that's why we need them to have a lifespan as long as possible of at least 1 million years, because the consequences of a leak or of a spill would be fatal. So we use the Weibull distribution system. And my colleague, he already said that Sweden and Finland are very good examples of deep repositories. If all the models and calculations show that the backup disposal package does not, or if the system doesn't work, we have a backup plan, and that's a copper container, which is used abroad. So we monitor what they are doing. We also monitor their licensing process and what they do. And now I think the best part of the presentation. In the 4th stage, we created a sample. We call it Odyssey. It was a rocky road because its construction was quite demanding. It wasn't easy. The faculty of mechanical engineering offered us a space for this disposal package. So you can find it here in this faculty. When you enter the building and if you go 1 floor downstairs, there is an exhibition right now, and you can also see this package there. You can see how robust it is, how big it is. It has the same diameter, it has the same structure and configuration as the real-life package. It's just smaller so that we can transport it more easily. And we will also very careful not to damage the floor in here. So we also put a special layer under it. And we had to be very careful also not to expose it to water. There are information panels next to the package. So you can also read about it and find out all necessary information. I recommend that you go see it because it will probably outlive us, I think, our entire civilization, I hope. Thank you for your attention. This is information, my contact information, as well as all the partners and project information. You can see also an interesting text about corrosions and information not only from our project, but also from others, and about other materials used, for instance, about copper coating used in Canada. And you can find out about the entire selection procedure and the process and selection of material and of the entire construction. Thank you for your attention. Thank you, Mrs. Lahodová. And now, does anyone have a question? There are no questions. Thank you once again. And let me give you also a present from the faculty bees. And I also would like to invite everyone, if you want to see this sample disposal package, we have an exhibition which is part of the Nuclear Days. The sample is not there. It's, if you go down one floor, it's downstairs, and you can also ask students that will tell you how to get there. And you're cordially invited to go see it. Yes, me too. I would like to encourage you to go see our Odyssey sample disposal package. And now about decommissioning of nuclear reactors, and our colleague is going to talk about the decommissioning of the nuclear power plant in Jaslovské Bohunice and the current situation.
Takže dobrý deň, dámy páni, dovolte, aby som sa vám predstavil.
Good afternoon, ladies and gentlemen. My name is Marian Vertoch. I'm the head of the division V1 in our decommissioning company, and I'm here with my colleague, Mrs. Rashnova, who works with me on decommissioning projects. So the nuclear decommissioning company is located in Jaslovské Bohunice, and it was established in 2005 when the Slovak power plants were privatized, and companies VIS and companies NPP V1 were established as individual companies, separate companies.
Takže kým sa nám to rozbehne, takže predstavím našu spoločnosť.
So before the presentation starts, I'll introduce our company. The nuclear decommissioning company is located in Jaslovské Bohunice and Mochovce. In Jaslovské Bohunice, we have 5 separate nuclear plants: a nuclear plant A1, which is in the decommissioning process, and then B1, also in decommissioning. Then we have a repository of spent fuel. Then we also have technologies and integrated storage in Mochovce. We have a final processing of radioactive waste in the vicinity of the NPP.
Na mape to vidíme. Naše činnosti je vyraďovanie jadrovej elektrárne.
So these are our activities: decommissioning A1 after an accident, then V1. Then we also handle radioactive waste. So we have processing plants On that, for that, we also handle nuclear fuel. Our company also has international commercial activities, which were limited by an act. For companies in the Czech Republic, Italy, and Germany, we were processing radioactive waste, burning for Italy and Germany. We're one of the 4 centers for collaboration with IAEA. So these are the activities that our company does, these 6 areas. As for handling the spent nuclear fuel, I didn't say that. We have a wet storage pools to store that waste. In recent years, we also stored Dukovany radioactive waste, and then it was transported to your dry repository. We're building a new storage because the capacity of the wet storage of the wet pools is reaching its 100%, so we will have to have a new storage starting next year. NPP V1, that's the first NPP of pressurized water of PWR that we had in the former Czechoslovakia. We started construction in 1972, and in 1978, the first unit was commissioned. Then in 1980, a second unit was commissioned. It's V230 reactor. So it's a predecessor of V213. The fuel is UO2, the moderator, and coolant, that's water. And there are 2 units, the overall output 4 times 220 megawatts. There was a small reconstruction in 2021, and in 1992. Then in 1996, we had a gradual reconstruction of the V1 NPP. That reconstruction continued till 2000. But in between, in 1999, the government of the Slovak Republic decided to decommission V1 as part of pre-accession negotiations before we entered the EU, because the Slovak Republic committed itself to decommission those 2 units. So we did that. In 2019, the final load of fuel was transported out of that NPP, and we received a license to process that fuel. The decommissioning of P1 is split into 2 stages. First of all, decommissioning of non-active facilities, such as the operating room, diesel generator, and so forth. In 2015, the second stage started. Originally, it should finish in 2025, but then we concluded that our estimates were too optimistic, so the final deadline should be 2027 for the overall decommissioning of V1 NPP. So we are in 2022. So we're doing works on the primary circuit, primary area. And in 2024, we should have a last project as part of the decommissioning. That will be decontamination and tearing down of the buildings, or the left buildings, some buildings will be demolished, others will be turned into commercial usage. So we're in D4.2, the assembly of large components of the primary circuit. In 2017, we signed a contract to implement that project. We're cooperating with Westinghouse in Sweden, Spain, and with Trnava company, Vuje. So in 2017, we were putting together documentation, initial reports, and time schedules. Then in 2018, the same stuff, documentation approval, implementation project. But we also started with the assembly works, such as thermal insulation. You can see the assembly of Kolpek. And we can move on. The main activities in 2018 were the work sites for the fragmentation of steel generators, then dry cutting, some storage space was built in 2018. Now we're in 2019. As you can see, we started implementing some parts of the project. And on this side, you can see the individual workplaces. The major works on that project should be finished in 2022, but we had to build more work sites. For example, 2 sites for dry cutting. So HCC and HUA work sites for dry cutting. And we also had to build pools for dry cutting to cut the pressure vessels and inner parts of the reactor. On the bottom image, you can see the PG cutting site. So that was for the control room and steam generators decommissioning. That's the space which was emptied after we decommissioned the steam generators. So we had 12 steam generators in the original operating room, and PG2 space was used for cutting of the steam generators, and it was hermetically enclosed. Then this year, we also transported all 12 pieces of PGs, steam generators, and the transport was partly sub-delivered by Škoda. So this is how we transported the steam generators out. So individual transporting sites and cranes, and a train corridor where we located it on a special handling device, and it was transported to the operating room for further processing. So all 12 steam generators were stored in the processing room in this manner. So the fragmentation and decontamination site started to operate in the previous year. That was a part of one of the previous projects. So it was cutting, fragmentation, pressure spray cleaning, and wet decontamination. So these are some parts of the implementation project to do wet cutting. So we had 3 existing walls and then created a pool of 1,200 cubic meters of water in that pool, and then we could locate those parts or components of the reactor in that pool and for the processing. You can see it on the animation. So sinking the components in the pool and then transporting it to a different site to be cut. And the components were then stored in baskets, but we'll show that to you afterwards. So this is an animation of the handling of the pressure vessel of the reactor. That animation is quite realistic because in reality, in real life, it looked just like this or very similar to this. So we're speeding up the video for the sake of time, and we'll stop the animation because we want to show to you the real life video. So we had work sites for dry cutting. So this is just a photo of cutting HUAs and HCCs. So next year, 2020, in 2020, as you can see, we completed the decommissioning and fragmentation of the primary circuit of the first unit, then the assembly of main closing fittings. So all the transport and technical handling had to be done. And since there was no maintenance, there were no maintenance staff, all of that had to be done by people from Škoda JS. So they provided both for the handling and maintenance. So the reactor was lifted and transported to the pool for wet cutting. This is a sample extraction, and this was part of the D42 project by Westinghouse. As you can see, the radiation situation was quite surprising because we expected to be worse, but then we were able to work there, so it went quite well. And then operation and commissioning of fragmentation from December to May. There was a trial operation. This is cutting. We call this Stargate. We use a special saw. We prepare the code of the steam generator, and with this robot, we step by step cut off the pipes. And then the pipes, once cut, we put them in barrels, and the barrels are stored in concrete containers and stored. There was no single contamination. The only contamination came from a direct contact from objects from the primary circuit.
This is the last cutting of the last steam generator. This is another video and a few pictures. This is preparation for fragmentation and transportation. Once the fragments are cut off from the reactor, we put them in yellow transportation baskets, and these are then sent through a packing machine, and in it you can see a container, and inside we put the yellow basket. This is where we put the yellow basket by a special equipment. It is in a centering station. The bell is put on it. The container is put inside. Then we have the packing station. That's how we call it. And once all water pours out, the entire bell with the inserted basket is then transported further. These are the walls of the container. Now we put inside the yellow one with components. On top, on that, first we seal it, and then we put a concrete container, and then the final one. So all these containers are then transported all together. There's another pooling container, which is designed for transportation, and it is brought to the internal storage. 3/4 were used for direct loading for VBK, and those that did not meet the criteria for utilization were stored in the integral storage. Let me try to open the pictures. So this is the packing station from the trial test, from the trial model. This is the pressure vessel with the yellow baskets where we put fragments. And with these did not have to be packed underwater, but directly outside of it. Fragmentation and volume compensation. This is what we did. Volume compensator is put around the heater parts. This is a fragmentation of a VECA reactor. So we used a special method, as you can see. And this is the end of the fragmentation of the main primary circuit. In 2021, we transported the reactor pressure vessel. Back then it was an exceptional situation because both pressure vessels were in the wet cutting pools, and both of these vessels were transported. The vessel from the unit 2 was taken first. This is probably not, what you see here is probably not used in Dukovany. There were special objects put put in the peripheral zone of the reactor. This is not used in Dukovany, and these packages are then put in the center for wet cutting, and because they are part of the primary circuit, so they had to be put in the pool as well. And after we finished fragmentation of the first unit, this is the active zone basket. You can see the configuration of components and the wet zone of unit 2. On the right side is the floor of the active zone and a block of protective pipes and the containment. Here you can see how we proceeded, how we cut it step by step. We also had to disassemble and fragment the reservoir for protection. That was for contaminated concrete, for instance. So we cut the concrete and then removed the contaminated parts. As you can see, using a saw, we made both horizontal and vertical cuts, and after that, the cut-off parts were transported in the baskets that you've already seen. The Unit 1 and Unit 2 pools are different. In the first unit, they are made of carbon steel, and in Unit 2, it was only stainless steel components. So the color of the water shows the difference. In Unit 1, it was green. In Unit 2, it was beautiful blue water. So that's the difference. Let's speed it up. It took a long time. The pressure vessel of Unit 1 was cut for a longer time. It took us longer. We were gaining experience. So we gained experience in Unit 1. And then we used all this in Unit 2, and then that was fast thanks to that. And now in 2022, today, we have completed the disassembly and fragmentation of the reactor pressure vessel. And this is the cutting scheme, the cutting structure. The fragments of it were put in the yellow baskets. Further on, we completed the cutting of the internal reactor components, and then all works completion. You can see wet pools of Unit 1 and Unit 2. You see the difference here. Right now, these centers are being cleaned. We drained out water. All these activities, however, are taking longer than we expected. The cleaning is problematic usually in Unit 1 because the water contains very small particles of carbon steel. And the particles are magnetic, so it's very hard to filter them out, and it takes longer than we planned. One of the very interesting activities was the disassembly of a bearing, and we put absorbers there and other metal parts we found in reactors. There were big concerns about this process. given that we had to make inventories of all the material and of the components, and the works went quite well. We got rid of the upper parts, then closed off all pipes, then we tore all the concrete parts and then removed the upper concrete part. Then all the pipes were emptied, they were completely cleaned and of course emptied. There were mostly absorbers and components that had to be cut and fragmented. This is how we worked with the pipes. I think that's enough as an example. Disassembly and fragmentation of steam generation was complete. As you can see, based on the posters, it was the last steam generator that was disassembled. And right now, as part of D42 project that was extended, so we are removing right now the activated concrete from the shaft of the reactor. And we found out that it's contaminated, the layer in there. So we have to also decontaminate and remove this layer to reduce and get rid of the contamination. Then we disassembled and fragmented the special water systems. I mentioned containers, and given activated and contaminated inner parts of the reactor or the reactor pressure vessel, we created containers, and they are stored in the integral storage. There are different dimensions, 80 millimeters, 150 millimeters. We added metal components. You can see different parts, such as the supporting coating, etc. We also, in this table, you can see which types of containers. It was 61 containers of medium level radioactive waste in the integral storage. There are also pellets that are waiting for further processing. There are metal materials with an activity which does not allow them to be released in a natural environment. So they also have to be stored.
So 2023, what is instead of us? The decommissioning of the active and contaminated concrete. We will also have to get rid of the warehousing pools and some of the storage sites. Then in 2024, the project should come to its end. And also the fragmentation and decontamination sites will stop operating because they were a part of stage D4 of the project. On the D4.2 site, we're doing the assembly of large components of contaminated material. We had over 2,000 tons of contaminated 2,200 tons of contaminated material, decommissioned and processed. So the efficiency of that site is 98.9%. That means that basically all the material is successfully decontaminated and can be used elsewhere in the natural environment. Well, this is just a plan. We can move on. One part of the metal material produced by the previous stages of the project are processed at other work sites in Division 2000, where they have the same lines for decontamination and defragmentation. Since 2024, that is next year, we should start the last project of decommissioning, which is called D 4.7. In that project, we'll decontaminate and demolish physical buildings. Then from December 2020, we've started a tender for this project that has not finished yet. And we don't see it realistic that that tender could come to its end soon, and that could be a risk to the completion of the whole project. So do we have questions? Well, the decommissioning costs money and also effort. A1 versus or comparison with VVER 440. Of course, I understand that A1 or A7 use natural uranium, A1. So if you compare A1 to VVER 440 and how demanding was it to decommission it? Is there any kind of comparison of decommissioning of A1 and VVER? You mean like financial comparison or works, the volume of work? It's like David and Goliath, like the giant and the dwarf to be compared. So when we decided to decommission this, the European Union provided roughly 60% of the budget that goes to the A1 and V1. There was an accident in the 60s. The fuel meltdown. So it's difficult to compare the decommissioning of a plant that had a history of safe operation and compare it to what happened on A1. A1 is demanding and challenging because there are alpha nuclides and there are leftovers of fuel, and well, basically 99% of activity of V1 has been decommissioned and moved to an internal storage. The activity of A1, an overall activity, is much lower, but the location is not suitable, I would say. You cannot compare these two projects. In my opinion, A1 costs more and it takes longer. They're planning to finish the decommissioning project, I believe, in 2035. And as you could see on some of the slides, so far we didn't have to use masks or any other protective equipment, while on A1 you have to do personal protective equipment. They're also decontaminating the steam generators, but the overall environment is not suitable for long-term work because of radiation, because of temperature. Those are small enclosed chambers, plus there's alpha radiation, so you cannot compare it. Yes, of course, the accident aspect is significant. If that unit did not have an accident in its past, maybe we could compare it. And if you take a unit of that kind and compare it with pressurized water 440, well, yeah, then we could compare it if we took just those two generally, but at present we cannot compare any existing units. Thank you. Any more questions? Well, my question goes to all panelists. The panel is called Decommissioning of Nuclear Power Plants. That's the title of the panel. So what I'm interested in is decommissioning or extending the life cycle or repeated commissioning of power plants if they were decommissioned for political reasons. For example, the 3 German power plants that were decommissioned in December and the 3 more that are still operating but planned to be decommissioned. And I'd like to know what the pluses and minuses are, whether it is possible or not, and for what reasons, just to get a realistic look on the issue. I apologize that sometimes I look like the know-it-all kind of a guy, and I feel ashamed, but I will try to answer because I worked in Germany for 6 years and I still have people that I know there and I'm in contact with them. The last statement of Minister of Economy Habeck was that the units, each of them having 1400 megawatts, those will be kept as backup till 15th of April. So it basically means for us practitioners that the fuel will not be changed. The power plants will be suspended, stopped. They will stop operations. And if not possible, then they can reduce their output to 50 to 60% for a limited time. The third power plant in Slant that will not be kept as backup, it will be fully decommissioned. And if the given region needs emergency megawatt output, they have 2 diesel generators to provide the emergency output or delivery of energy. The Bavarian Prime Minister was against that because he wants to keep the 2 other blocks operational. But we know that it doesn't make sense to have it all done in one campaign. It's all about extending licenses. Some of the components will have expired licenses as of the end of December. Also, they have not ordered fresh fuel yet. So I just can't imagine that it would be as easy as our media presented. And also, the distribution companies stated that their distribution capacity for the transport of electricity has been booked by other suppliers. So that discussion between the producer and distributor has not happened yet. So if you look at the overall context, it is not realistic to expect that the 2 units would be put back into operation. It would have to be a crisis situation, really, and then they might be commissioned for maybe a couple of weeks only, and that will not solve anything. Of course, the decommissioning of the German nuclear power plants caused the energy problems in our country as well. But we have to realize that they do not impact the energy price on the stock exchange in Germany, in Leipzig, they might impact 5 to 7% of the prices, but the rest of the volume of energy and the trades are forwards and futures. So Czech and the Slovak power plants have sold their energy for 2 or 3 years in advance. So whatever they will generate for 2 or 3 years from now is already sold. Saudi Arabia, by the way, already sold its oil for up to 2031. So these forward trades are quite common on energy stock exchanges. Okay, thank you, Professor. I think we had to hear that. Well, that was a perfect explanation, but just a small detail. When the Greens were exerting pressure on those operating the power plants, they did not realize that when you have a unit which is getting close to decommissioning, there's a phase-out stage. But they did not realize that when you decommission a unit and try to recommission it again, it is a completely different process, especially if you want to operate it on output effect. You probably remember when we had the first gas crisis in 2008 or 2009. At the end of 2008, we closed down one of the units, and then in 2009, that was the start of the gas crisis due to Russia. And we were decommissioning that unit from roughly 80% of output. And what we thought was that we can put it back into operation with one turbine only, and the output on 50%. But we didn't have to do it, luckily, for one reason. The legislative paperwork around it is so complicated that there would have to be measures, not only technical measures, but also legislative measures. So for the nuclear authority in Slovakia to permit the recommissioning, there would have to be many criteria met, plus we would have to do all sorts of trials and renew our licenses, because many of the trials and licenses expired. So politicians believe that within a couple of weeks we can put units of NPPs back into operation, but that is not realistic. That would have to be a highly extraordinary situation, emergency situation, technically and politically. Okay, do we have any more questions? So when it comes to the controlled aging of concrete, you can discuss it with Mr. Krinsky over the coffee break. So thank you to all the speakers. Thanks to all of you in the audience, and I'll be looking forward to see you again in the future. So we agreed that, well, because we ran out of time, so we will not add that presentation that we missed in the previous panel. Now it's 1:30, so it's time for another coffee break, and we will resume at 2 o'clock.
for cleaner and healthier energy that the world wants. KHNP is growing with the world. A global energy company, Korea Hydro and Nuclear Power. KHNP is South Korea's largest energy company. From the first to the greatest and the best. The early challenges KHNP took on were the first steps forward to producing better energy and have now become great steps in the history of energy production. KHNP is a global energy company. A company replete with solid corporate assets, an excellent talent pool, and global recognition. By distributing advanced technology to various points around the world in need of electricity, from power plant construction to operation solutions, KHNP is positioned to become the world's leading energy company. KHNP is the leader of the future energy industry, enriching life with eco-friendly energy. KHNP continuously invests in new and renewable energy and R&D. By achieving technological innovations through integration with the fourth industrial revolution, expanding its overseas business and new energy business, KHNP is preparing for a new future. A total energy company that grows bigger through change and innovation. A company that constantly challenges itself for a better tomorrow. KHNP is leading the global energy industry. A trusted global energy leader. Korea Hydro and Nuclear Power.
Společnost UJV Řeš navazuje na více než 60 let zkušeností svého předchůdce, Ústavu jaderného výzkumu. Společnost dnes prezentují špičkoví odborníci, technicko-inženýrské a projektové služby, aplikovaný výzkum a unikátní technologická infrastruktura. To vše ve službách bezpečné a spolehlivé energetiky, průmyslu a nukleární medicíny. K dnešní klientele z celého světa patří hlavně provozovatelé energetických celků, státní dozorové orgány, investoři náročných průmyslových technologií, původci radioaktivních odpadů a pracoviště nukleární medicíny. Jedním ze stěžejních úkolů UJV Řeš je podpora bezpečnosti a spolehlivosti jaderných elektráren v České republice i ve světě. Z legislativního hlediska jde hlavně o průkazy jaderné bezpečnosti zařízení, z provozního pohledu je to škála aktivit zaměřených na sledování, kontroly a vyhodnocování provozních parametrů, jejichž výsledkem jsou návrhy konkrétních opatření pro zvýšení bezpečnosti a spolehlivosti provozů. V oblasti palivového cyklu se specialisté z Řeše soustřeďují na podporu licencování paliva pro reaktory a jeho efektivní využití. Zvýšení efektivity paliva v provozu bloků řeší UJV Řeš zejména vývojem nástrojů pro optimalizaci palivových vsázek a programů pro monitorování aktivní zóny. Řízení životnosti jaderné elektrárny představuje propracovaný systém péče o složité technologie různých typů. UJV Řeš se touto oblastí zabývá i na mezinárodní úrovni, zpracovává programy pro řízené stárnutí konkrétních komponent, je autorem řady certifikovaných programů a metodik. Základnu pro řízení životního cyklu tvoří zkoušky mechanických a strukturních vlastností materiálů, hodnocení jejich degradace v náročných podmínkách, svědečné programy tlakové nádoby reaktorů nebo kvalifikované inspekční metody a postupy. Podporu provozovatelům zastřešují komplexní projekty řízení životnosti a zvyšování výkonu průmyslových celků. Akreditované laboratoře společnosti působí v oblastech pokrývajících vybrané vlastnosti materiálů, akreditovaná zkušební měření, zkoušky a analýzy.
Jsme Doosan Škoda Power. Už více než 100 let vyrábíme špičková energetická zařízení. Jsme světovým dodavatelem systémů turbogenerátorů, komponentů a služeb v oblasti projektování a výroby. Využíváme nejmodernější technologie a neustále do nich investujeme. Patříme ke spolehlivým zaměstnavatelům. Významně podporujeme vzdělávání a rozvoj našich zaměstnanců. Rozsvítili jsme miliardu domácností po celém světě. Jsme Doosan Škoda Power. Roztáčíme svět kolem nás.
Since the beginning of the 1980s, we at Fortum and the VTT Technical Research Center of Finland have been developing APROS, a comprehensive, accurate and user-friendly software product for modeling and dynamic simulation of power plant processes. Using only one code, you can simulate operations of the entire power plant or specific isolated processes for a variety of engineering and training purposes. One code comes with many benefits: savings in purchasing computer codes, model design and maintenance. It increases the accuracy of the simulations, as there is no need to handle the integration of different codes between different models. High accuracy is also ensured by reliable solvers, extensive models and component libraries validated by nuclear industry standards. When planning a new or upgrading an existing plant, APROS helps you test different design solutions, find optimal control and process equipment parameters, and even test the real INC cabinets before their installation. The model, developed for engineering purposes, can be used for building a training simulator, saving money and time. Models are built utilizing an easy-to-use graphical user interface, and model parameters can be changed during simulation. Programming skills are not required. It's enough that the model developer knows the processes which are modeled, and if necessary, APROS can be easily integrated with other codes. We at Fortum want to share our knowledge. For further information regarding APROS, please contact us.
Vydavatelství Publishing představuje svůj hlavní titul. Časopis Průmyslové spektrum, nejčtenější strojírenský časopis, který přináší aktuální informace o domácích i světových trendech v jednotlivých odvětvích oboru. Časopis je určen pro střední a vyšší management, konstruktéry, technology, pracovníky výzkumu, vývoje i pro učitele a studenty vysokých a středních odborných škol. V jednotlivých vydáních měsíčníku Průmyslové spektrum se náš silný tým zkušených odborných redaktorů zaměřuje na průmyslové obory, které jsou v České republice silné a mají potenciál růstu a reflektují změny v ekonomice a v různých oborech podnikání. Hlavní pozornost je věnována výrobní technice a technologiím, které jsou nositeli inovačního pokroku a zrcadlí se v nich výzkumně vývojové milníky nedávného období. Velký důraz je kladen na kvalitní a zajímavý redakční obsah a edukační dosah. Přinášíme reportáže z výrobních podniků, vedeme hovory s osobnostmi českého průmyslu, tlumočíme názory odborníků z výrobní i akademické sféry. Věříme, že tímto náš časopis přispívá k osvětě strojírenských oborů a k jejich popularizaci mezi širokou veřejností. Vydavatelství Publishing, to jsou inovace v průmyslu, strojírenství a výzkumu pod jednou střechou.
Good afternoon, ladies and gentlemen. It's past 2 p.m. People got stuck at lunch, but I hope everyone will get back. Let me introduce the chairman of our last section. This is Mr. Fiala. Everyone knows him from the turbine industry. He will be moderating this section. Thank you. Thank you for the introduction, ladies and gentlemen. Let me start the 5th section, turbines for nuclear power plants and heat extraction for district heating. I would like to ask now Professor Slugeň to make the first presentation. Good afternoon, everyone. I'm not really an eligible member for this section, but I tried to prepare something related to the topic of turbines, because my presentation is about extending the lifespan of nuclear power plants. Only 16% of the world's resources is low carbon sources. So it's 1/6. It's not much. As you can see the pie chart, it shows the electricity production. 2/3 are fossil fuels. And as you can see, out of the low carbon sources, 16%, 1/4 in the world are nuclear power plants. So when someone asks, what are they good for? They can be either good to produce electricity in a low carbon way. I don't say a zero emission way, a zero carbon way, because during the process of enriching uranium or melting steel, there's always some carbon. But the footprint, carbon footprint of carbon nuclear power plants is 3 times lower and for wind plants and twice as lower as solar panels. If we have enough energy, we can live longer. That's a fact. So where there is enough energy, we live longer, we have a higher comfort, life comfort, and better lifestyle. But we should realize that at least 2 billion people in the world don't have electricity. Why do I talk about low carbon energy sources? Let's look at this chart. Scientists like to use charts and tables. So using one, from 1860, which means the increase of temperature was 1 degree. As you can see, the tendency is not decreasing. If we want to mitigate this increase and slow it down, we need not only renewables, we need also low carbon or zero carbon energy sources. You might say that these are cliches about global warming and climate changes, but when we think about the level of oceans going up by 8 centimeters, there will be no Boston, there will be no St. Petersburg, there will be no Venice, and 100 million people will have no place to live in. So what is the importance of nuclear energy? It's 10 million times better in terms of potential of generating electricity. And in comparison with gas, oil, there is a 7-order difference. In the world, there are about 444 NPPs. These are commercial NPPs producing electricity. At the same time, there are about 20,000 reactor years of experience, operational experience of nuclear power plants. So in the past, when I showed this chart comparing perspectives of the new builds, generation 3+, people kept talking about the power output and the construction time and whether it's 60 months or more. But let's talk about efficiency. And the efficiency is highest in the boiling water reactors. And that's quite logical because you don't have a primary circuit, so the steam from the reactor goes directly to the turbine, and the efficiency is 38% at the best, in the best case scenario. VVER had 31%, PWR had 38%, and Czechoslovak had 20%. There could be also high temperature reactors. There the efficiency would be around 41, 42%. And then there are supercritical water reactors of 45 to 48% efficiency. The average one in PWRs is about 38%. The age of operational reactors is becoming longer, and their lifespan and life cycle is extended. People extended from 20-something to 30, then to 40, and we keep extending the life cycle. And so using the irradiation embrittlement, we talked about 40 years. Now we talk about 60 years. In Florida, they even extended the life cycle to 80 years. And soon enough, it will be 100 years. And maybe the limiting factor will not be the life cycle of the vessel, but of the concrete shaft. This is quite strange. Right now, we are putting in operation a third unit in Mochovce. It's VVR 440, and it's for 60 years. So the first concrete base was put more than 30 years ago, so it will be altogether 100 years. But as someone says, there is a transient period for all the decommissioning and licensing, so that's extra, 10 years extra, so it's 110 years. And in terms of decommissioning, yeah, this is a great solution. I would like to praise them. That makes it 120 years of life cycle. Do you realize that? Nuclear energy will always be nuclear energy, and it will always be here. I talked to a Turkish lady, and we discussed the fact that Turkey considers deep repositories. They have VVR reactors, and that it's still far away for them to have a deep repository. But I replied to her that it's the same as if you say someone is a bit pregnant. You cannot be a bit pregnant. And the same goes with nuclear energy. So once you have nuclear energy, you have to consider everything that goes with it, all the costs that go along with it. Even if you have one fuel cell, $200,000, the costs for the storage and the long-term storage are 6 times higher. So you have to have money not only to buy a fuel cell, but also you have to have money to store it and to put it in a repository. So after I said this, the Turkish lady was a bit sad. And she said, you could use a lease or something like that, and it could be a solution. Well, that's not a solution, because there will be high-level radioactive waste, and you will still need to build a deep repository anyway. And now the thermal balance of VVER 440, as stated by the suppliers project. If someone says that we are far beyond 1,375 megawatt, that we increased the fuel loading and the costs and extended other factors, and we can also have a turbine and gain megawatts in that part, in the turbine. But if you look at 1,375 megawatt, the plant nominal power output has already been reached, and we have already had 1,520 megawatts of power increase. We've seen it in Dukovany, and it will be the same in Mochovce. So if you look at the picture of this VVER 440 reactor, there are losses, but also returns. But the biggest losses are in the condenser and during the change and the transformation into heat. So the consumption of heat is about 382 megawatts, but this has changed over time a lot. We have higher reactivity of the reactor, which means that even with a minimum coefficient of the load of the reactor, we can still have 2,100 megawatts. But how do we transform this further? We have to change the blades of the turbine, because the turbine is the place where you can get some gains. So you have to change the blades. You have a better condenser. You have a better vacuum in the condenser. That's also a way. So by optimizing all these steps, you can increase the adiabatic gradient and optimize losses. For instance, there are turbine losses, generator losses. So you multiply different losses. It can be just 0.98, but if you multiply them, they become important.
So if you want to get the most out of that power plant, you have to minimize losses and you have to optimize the output of the turbine, because the turbine is decisive for the final output. The temperature of the circulation cooling water. That's a problem that people often do not discuss and don't know much about. It works by 2% better in winter than in the summer, because the water that goes from the tertial circuit to cool the condenser is colder. So if you have warm water, even if you increase the surface of the condenser, for example, in Bohunice, from 29,000 pipes, they had 33,000 pipes in the condenser. So they increased the surface of heat exchange, and that determined the final output. So the temperature of the cooling water is very important, and the nominal output can be achieved. The ideal one can be achieved if you do not exceed the cooling water temperature of 22 degrees, but that is not often achievable. So if the water exceeds a certain temperature level, you cannot achieve nominal output. In Mochovce, we cannot have a fifth unit because we don't have enough technical water, not just for a standard operation, but for a 100-year maximum. And of course, in emergency situations or accident, you need to have much more water. And that's why we cannot have the fifth unit in Mochovce. And the situation gets worse, because even in Mochovce, we take technical water from River Hron and Levice and Vrable, the municipalities and the cities. They take water from the river, and the cities grow. And we want to live more and more comfortable way of life. We need more and more water. And water itself becomes a problem. Why? Because I need to cool down my condenser to an optimum level. And if I don't cool it down to an optimum level, I lose output. And that's what happens if I don't have enough water and enough cold water. Output goes down. So if I want to increase the output, and the Czech Republic and Slovak Republic were We're a small country, so we have to be reasonable. Large countries like India or China, they don't have to be so reasonable in managing their water resources. We have to be. So how do I increase the output? For example, I can increase it by 2 or 3% just by more precise measurement. For example, when I measure delta T on the reactor, the project design talks about 28.5%. Now it's over 30%, and I have 217 thermal sensors on the output side of the active zone. But that thermal couples, they age, and after 5 or 7 years, we have to replace them, because that aging means that they don't measure properly. That's why we have 217 of them to make an average of all the measurements. But that was my first thesis that I was heading in 1990, when with the students, with that student, we calculated the average value from the thermal couple, and basically by that we set the standard procedure for measuring. And if you have a half a degree difference by improper measurement, you lose something like 40 megawatt in energy. So 40 megawatt, that's not little. So try to make your measurements more precise and reduce your tolerances, because you always consider the worst value out of those measured. So if you have more precise measurements, you can gain certain megawatt hours by being more reasonable and measuring better. But that will not gain more than 5% of the output for you. So I rather focus on modifications on the secondary of the secondary circuit, because I can gain up to 20% of output, increase of up to 20% of output. Well, I wanted to show something new also in my presentation, and so I focused on the life cycle of units VVER 440 and V2. That's the third unit in Bohunice. So I'd like to say a few words about the usage of simulations to extend the life cycle by calculating nuclide vectors. Well, actually, I will skip the calculations because you have the whole thesis written on that, how to measure all those parameters, how to determine the uncertainty values and so forth. So on this chart, you can see the decreasing curve showing the flow of neutrons as it goes down with the increasing distance from the active zone. And of course, Monte Carlo is a code. It's a code which is based on Monte Carlo principle as a source element. And the result of that is this detailed table and these curves. And you can see that after 60 years of operations, you can achieve a certain level of activity. And you can see that it doesn't really matter if the operations last for 3 years or 60 years, the result is basically the same. And do you know when the costs of decommissioning of the third unit in Mochovce go up within 1 minute by 1.4 billion euro? In the moment when you successfully conduct a physical experiment, when the new generation of neutrons will be the same or a bit higher than the previous generation. At that moment, your nuclear plant under construction becomes a nuclear plant which is subjected to all that legislation for decommissioning. And we heard in the previous presentation that a decommissioning of such a kind of a unit costs 1.3 billion. So that's when the price or the cost of decommissioning goes up before the activation of fuel. That's what the ex-Prime Minister of Slovakia, Mečiar, invented. He was the first one who started calling it activation of fuel when he promised to the Austrian Chancellor that he will not give a permit, he will not permit the activation of the fuel. But once you activate the fuel, you have to follow all the procedures for the decommissioning, just as we saw in the presentation of Yavis, because once you activate the fuel, your nuclear plant becomes a nuclear plant after activation of fuel. So that's what I meant when I said that you cannot be half pregnant. So this is the decrease of individual nuclides when it comes to concrete. Because, well, I focused on pressure vessel for 20 years, but now concrete is a fashion. And the quality of concrete and the life cycle of concrete, of course, depends on how it was used, according to what standard it was produced, whether or what humidity is in the environment, and whether there is nuclear activity or not. And we discovered that up to the level of fluency times 1 on 19, the concrete can withstand basically everything. But of course, it's mainly because it's reinforced concrete, reinforced with iron 55. And that gives it the strength. And then you can stop with nickel 63, which has something like 96 years of half-time. Concrete, which is some 362 centimeters away from the active zone, can be freely released. And also the strategy of delayed decommissioning is, in my opinion, a dead-end street. A fast decommissioning is better. And so when you're decommissioning the pressure vessel on other components, we have to take into consideration other elements like cobalt 60, which has a relatively high radiation factor, high energy gamma, 117, 130, 33, and that is much more negative than nickel 63, and cobalt 60 has a release level by 3 to 4 orders lower than the other particles and the other elements. So that's all on my side. Thank you for attention. Well, thank you. Do we have questions? So, Professor, I have a question. I would like to know what you think about nuclear fusion and its future as an alternative. Do you think that realistically it could be used in time? Well, thermal nuclear fusion has gone through a long development. Physically, it was proved that it's possible in 1958. So to give you a short answer, I will quote a Russian child encyclopedia from 1973. Mankind will use thermal-nuclear fusion only when it really starts to need it. And I think the time has come, but technologically we're not yet prepared. It's far away in the future. ITER in Kadarash should have produced the first plasma in 2018 and a pulse operations in 2027. And I think they will not have the first batch of plasma in 2027. Then there's a demo planned for 2040, and then Proto as prototype, which is planned to operate in 2050. I knew the deadlines long ago, but they keep moving on the timeline to the right. It's a constant drift. It's an excellent technology, but we have to invest not only money. That project is exceeding 20 billion euro over the budget, but we have to have the will and effort to complete the project. And that's what's missing. So we're on the first name terms from yesterday. So yesterday, or today as well, you talked about decommissioning costs. It's something like 1.3 billion euro in Slovakia. And if you could compare it to construction costs, because everybody keeps arguing that nuclear energy is expensive to build and to decommission. But looking at our example of decommissioning, it proves that it's not so expensive. Well, the devil's not in detail, but in time. So when we calculated costs of building a deep repository in our Slovak agency, in our nuclear fund, the hole in the ground costs something like 3.7 billion euro. But if you build it beyond 2060, the cost will increase to 20 billion euro. So when V1 unit was built, the cost of construction was 10 billion Czech crowns. Can you build a new unit in Dukovany for that cost today? Certainly not. But the decommissioning costs have to be accrued in time. And we do not know inflation even for next year. So not even the best economist will give you an answer, because there are so many unknown variables and factors that it's impossible to say. But the debt service is what is a plus for small modular reactors, and it's a disadvantage of large NPPs. You have to borrow the money to build the units. That may last 20 years, maybe longer. So you borrow the money on a loan. You have to pay not only repayments, but also interest. So that's the debt service. And if you repay it over 30 years, then you pay 3 times as much as you borrowed in the beginning. So if it's in the order of million of whatever, crowns, units, euros, then okay. But if it's billion of euros, then to pay 3 times more than I borrowed, that's just too much. So the financial model is what kills nuclear energy. Thank you, Professor. And just like any other speaker, you will receive a present from our bees. So the next speaker is Mr. Shimurda from the Academy of Sciences.
And the presentation is called Experimental Modeling in Transonic Flow in Internal Channels of Turbo Machines. Thank you for the invitation. My presentation will give you an overview of activities taking place in the Institute of Thermodynamics in our laboratory. And all of the experiments are related to the operation, whether directly or not, of turbines used in nuclear power plants. This is the outline. First, we'll mention several experimental methods. It will help you to see the measurement methods as well as the equipment and facilities we use. Then I'll mention high-speed wind tunnels we have, and then specific topics we dealt with. The first slide shows the main categorization of measurements in fluid mechanics. Mostly we want to know the field pressure and the speed pressure. Pressure field and speed field. With speed field, it's more difficult. We have to measure other factors and then calculate the speed field. We can use pneumatic methods such as different probes, and we can then determine static pressure, total pressure, and then calculate speed. And if there are several openings, we can also determine the flow direction. Probes also affect the direction, and the reaction of the probes are often delayed because we try to use smaller probes. Then we also use optical methods. We measure velocity of tracer particles, such as LDA and PIV, depending on the quality of the tracer particles, and they should ideally have the same density as the liquid. Then we use classic methods measuring the refractive index. So these methods measure density, and based on that, we can calculate the pressure field and later on the speed field, the velocity field. They do not affect the flow field, and we can also use them to measure fast phenomena. And the third big group is the so-called hot fire anemometry. We measure heat transfer depending on the flow direction. And again, these are intrusive methods, but they have a very fast response. There are other methods such as pressure and temperature sensitive paints or acoustic methods, but we don't use these. Now about our lab, most of you know, we have two aerodynamic tunnels. At the end, there is a high under pressure vessel. We suck air out of it, and air is then sucked through the measurement space. And thanks to the underpressure, we can get high pressure ratios, and we can reach the Mach number in test sections, maximum Mach number. This is a former gold mining shaft, and thanks to the large scale and large size of the shaft, we can measure for a time of 60 seconds, which is quite unique because usually in other tunnels you can measure only seconds. The attainable pressure is about 10 megakilopascal, for 5 hours. There is air from the outside being brought in. The air has to be dried out, otherwise there would be condensation of the air humidity, so that would ruin our experiment. The first tunnel is the heart of the lab because we use it for blades and lattice. This was designed in Škoda Plzeň and manufactured in Škoda Plzeň. You can see the entrance nozzle, which can be deformed. Often you need to use a supersonic inlet nozzle. You can reach Mach number before the lattice. It is wide, 160 millimeters. The Mach number is from 0.2 up to 2. And we measure 2D cascades. We use traditional optical methods. We use the Mach-Zehnder interferometer and also a device for Schlieren optics. These are the aerodynamic parameters of the cascades. We use a semi-automatic traversing device with digital measuring, and we can thus test the 3D field. The main purpose of this tunnel is the measurement at the cascade for 2D cascade research. We researched about 160 transonic and supersonic turbine and compressor cascades with the help of Škoda Plzeň. We used peak profiles recently for steam turbines of high power. As you can see, the geometry in these cross sections, they are very specific, and the channel or tunnel between the blades is very small, but what happens there will affect the entire power field or the flow field. Some of the profiles use the supersonic regime at the inlet part, but there are some issues related to that. We also measure compressor cascades and turbine cascades at extreme incidences. We saw several interesting phenomena, such as the unstarted supersonic flow. Some of them used supersonic speed before the cascade, and then there is a normal shock wave before the turbine, before the blade. So if this happens, the inner branch of front shock wave is a normal shock, then it's an unstarted supersonic flow. If we lower pressure, the internal branch of the shock wave will become narrow. And in that case, we call it a started supersonic flow. The problem is that there is a gap between these two, an unstable state with different Mach numbers, and as you can see, the pictures are very different, and the oscillation can lead to fatigue of the blade, because in the small channel between blades, this small movement of the shock wave affects the entire flow field here in this part, but in this part as well. So then you see this fatigue on this curve, and at this Mach number, the load is oscillating a lot and is very unsteady.
So to research into what is happening, we have a pressure sensor with fast response, and we also did some optical measurements. You can see the non-started situation, and when we looked at the frequency characteristic, we could identify the peak with roughly 1 kilohertz, while in the started supersonic flow regime, the wave sort of sits beautifully in one area of the chart. There's no peak. So all these blade cascades, and when we do research, we're looking into 2D problems, but we also look at 3D problems. For example, here we looked at the aerodynamic effect of typos in extremely low turbine blades. There's a barrier in flow which causes problems. We looked at when we measured it thanks to traversing device, and you can see that typos increases the losses because it's deforming the shape of the blade or the shape of the flow behind the blade. So the measurements were done by people from Škoda Pilsen, and we were not able to calculate all the typos outflows, but Tomáš Radnic did some calculations. So this is one of the outcomes. This is lambda 2 criterion, section of outlets, CFD at the bottom, and shock waves above it, the visualization of the shock waves and vortices. And my colleague, Mr. Radnic, is trying to analyze that flow field, and he tries to come to some meaningful conclusions. We also started doing some measurements using pressure-sensitive paints. That's what I mentioned in the beginning. So you have a coating, a paint with luminophorous particles. So you apply UV light, and then these particles emit red light. So, but if you have too much oxygen in the air, then the emissions go down. So with the lowering of the pressure, air pressure, also the share of oxygen in the air goes down. So when you have less oxygen, you have more emissions. We measured in an environment with M equal to 1.9. This is an interferogram with shock waves and a slowdown in the valley of that curve, and then expansion again. So on that interferogram, you can see a 2D flow field, which corresponds to the measurement on the wall of the tunnel. But in the tunnel, you have certain threshold layers that influence the field, and it's not really 2D. And thanks to the pressure-sensitive paints, you can see what impact the walls have. There are some traces of the shock waves, and you can see how the shock wave interacts with the layer on the side wall. Now, here you can see the comparison of various M numbers, Mach values, and there are differences due to the fact that the interferometry integrates the values from the whole width of the tunnel, while with the pressure-sensitive paints, we measured in the center of the valley. Then we have a second tunnel, so-called modular tunnel, which is a regulation or a control device, transonic modular wind tunnel. We can basically configure any measuring environment that we need. So, for example, we measured a radial cascade in the past, which allows for optical measurements and traversing. And 10 years ago, we also started cooperating on the research of flow in high-speed wind tunnels. We had 2 intercepting valves here, 4 governing valves, and 1 overload valve in this assembly. But basic measurements were done in Kladno on their model valve, and we did a visualization of the flow swirl downstream of the valve. The main objective of the measurement on these valves is to find out what various modifications of the valves would have on the operating parameters. So we modify the beta curves, and we also measure pressure pulses below the regulation valve, and then we generate these maps where the curves show areas of higher pulse and lower pulse. Another application that we used this for was the measurement of compressible fluid flow through narrow channels. The channel length is 100 millimeters, channel width roughly 100 millimeters as well. And we wanted to find out what the distance, or how the distance influences the arisal of turbulences. And also we looked at the coating of the individual walls and other features of the walls, for example, homogeneous coating or 3D coating. Together with Mr. Lepichovsky, we designed and manufactured this measuring area, which is quite modular, and we're measuring compressible fluid flow through narrow channels in this, and transonic flutter in the blade cascade. The blades can rotate, and that simulates the torque rotational movement. We have pressure sensors with fast response, and what you can see on this chart is that there is a pressure wave. And if we look at a longer interval, we can see that the pressure wave does not occur every time. So there are interesting phenomena happening, and we're in the phase of analyzing it. That project is performed together with Technical University in Liberec, Mr. Shidlov and Psota. And thanks to modern laser interferometry, they were able to take interferograms of the flows. In the classical interferometry, to be able to do the imaging, you have to have high quality glass. In this case, we have 4 holes and a plastic glass. We're using that also because we often have to suck out some liquid layers on the side walls of the channels. So let me show you a video at the end of my presentation. This is the compressor cascade, and the oscillation level is 200 Hertz and Mach value of 0.9. So the starting Mach is suprasonic, but afterwards it turns into supersonic, and the supersonic area is closed with a shock wave. and that's moving in that field, as you can see it, and the shock wave is moving forward through the subsonic flow, subsonic wave. So if we calculate the speed, it's roughly 1.08 Mach. So that blade generates pulses in the channel that keep repeating. So that's all on my side. Thank you. And I'm looking forward to questions.
Any questions? No questions. All right. Thank you very much for that.
Takže další příspěvek má pan inženýr Peterka.
And the next presentation will be given by Mr. Peterka, about 50 years of experience of turbine manufacture in Škoda, turbines for nuclear power plants. Ladies and gentlemen, good afternoon. I would like to continue after the interesting presentations that we've heard. My name is Jan Peterka, and I would like to talk about our 50-year experience in nuclear energy. In the first part, we would like to introduce our company, Doosan Škoda Power. I would like to mention several installations that we've made in the past 50 years. And in the last part, I'd like to introduce some new technologies for nuclear power plants. Doosan Škoda Power, who are we? I would like to present us with this slide. We are one of the top 3 suppliers of turbines for nuclear power plants with a power of 50 to 100 megawatt for plants with an installed capacity of 3 gigawatts. And our turbines can be found all over the world in almost 60 countries all over the world. Here in the West Bohemia University, I would like to stress the number of employees in our company, because over 40% are graduates of this university. That is a big and important number. Our history goes back to the 19th century, 1869, but the more recent history that I'd like to mention was the manufacture of the first turboset of 200 megawatts in 1966. Another important year was 1992, when we manufactured the first turboset for a nuclear power plant of 1000 megawatt. And this set was later modernized. And that was for the Temelín nuclear power plant. We react and respond to the demand of the market and the requirements of the market relating to lowering carbon emissions. So the advantage of our turbines is that you can install them not only in coal power plants, but also and especially in for biomass plants and waste management centers. That's the largest number of our projects. There are also solar plants and other technologies where you can find our turbines. New drivers are the modern technologies. And from this slide, I would like to mention SMRs. we see them as a huge opportunity for the future, and we think not only in Škoda but in other companies, people see a great potential in SMRs. Our projects do not end with the installation of the turbine. We strive for continuancy, and we strive to be active and follow up on the projects. We have long-term service agreements with our customers where we deliver our turbines. These are long-term agreements where we carry out small and large-scale inspections. During the small-scale inspections, it looks like a normal inspection of basic operational data. We check for some defects in isolation. We check all the bearings, valves. We exchange parts that need to be exchanged. And then we also carry out large inspections, which are almost like general inspections. During these, we open the turbines and we make detailed checks of all the critical parts of the turbine. We recommend repairs of various components and parts of the turbines. The long-term service agreements are also supplemented by a hotline service, which means that the customer can reach us 24/7. The customer can get a support of our operators because we use a remote monitoring system, and we can remotely see the operational data of the turbine. So the colleague, if the customer calls them, sees the same screen as the customer in the plant, and that helps us a lot when we have to deal with some operational defects. And thanks to that, we can easily talk with the operator and help them. This slide shows the rich portfolio of the turbines we offer. We can supply small-scale turbines on frames. The power can be a few megawatts. Such turbine has the oil system, and it's a very simple supply also in terms of installation. But then, of course, we also offer large-scale turbines of 3 bodies, for instance. As I already said before, our installed capacity is over 35, 53 and more gigawatts. You can see here the distribution on different continents. Europe is the most represented continent, but we are also present in South America, in Africa, in Australia. These are installations that we have done so far in nuclear power plants. We were active in NPPs in both Slovakia and the Czech Republic. One of the latest projects we had included the modernization of a turbine of a foreign manufacturer in Finland. The project was called Lovíza. Most of the Czech and Slovak plants were already modernized throughout the years. And what do I mean by modernization? In most cases, modernization means a complete replacement of the flow part, because we want to extend the life cycle of the nuclear power plant, and if we use the latest technologies, whether it's 3D blades and new materials, 3D blade profiles, also all together with the inspections, and we also strive to use new technology and the latest methods available also in order to increase the efficiency of the turbines.
So the small modular reactors, SMRs, that's an area where we see many opportunities, and probably not just us. We're in close contact with the future developers and future suppliers, such as NewScale, Rolls-Royce, New World. NewScale and Rolls-Royce visited our company in recent months. What is interesting for them, and generally for these suppliers, are our experience, our 50 years of experience in the nuclear business, our know-how, and also the output range of our turbines. And the installed turbines in the Czech Republic and in Slovakia amount to, well, we have 16 turbines in the output range of 220 megawatt after modernization of up to 240 megawatt in electrical power. And there's one very interesting research and development project in Canada called Chalk River. So we're active there as well. So it is not a long future ahead of us. It's a foreseeable future that we're dealing with in our R&D department, and we try to support our future customers. And just as I have said before, as part of the long-term service agreement, we offer remote monitoring service, remote monitoring system. It's also called Turbo Life Care System, which makes it possible not only to do the standard monitoring of operational data that you have in your control room. We can also do other types of measurements, such as blade tip timing. You could see it at our stand where we demonstrate that. We also do REMS measurements, erosion modules, and so forth. These are new modules for measurements that we try to incorporate into our standard monitoring service, the remote monitoring service, so that we extend the data on the turbine that we provide to the customer. For example, the remaining life of the turbine, when it is going to be necessary to open the turbine and replace some inner parts and so forth. And what you could also see at the stand in the hallway is an flow of steam in the turbine and measurements related to it. Of course, there must be some prep work done. So there's a flange that you have to open on the turbine and insert a sensor, and then you can measure the humidity and the size and intensity of the droplets falling on the blades and so forth. So wetness profiles, droplet size, spectrum, turbulence, velocities, pressure, all of that can be measured, and our software and calculations can be then updated based on the measurements. So this is a service that is more and more demanded amongst our clients, and not only clients that we provided, that we delivered turbines to, also other clients. So thanks to the checks and inspections that we do on site, and thanks to our close contact with the operators of our turbines, we try to use the gained data, the collected data in research and implement it in research and development. Be it data on materials or various structural modifications, the valves and flaps used in NPPs, and generally the parts of turbines that we deliver. So from the point of view of deliveries to the nuclear business, what is important when it comes to operating parameters? Moisture extraction, at least from the latest stages, LP stages. You can see the distribution blades that we manufacture. If we need them, if the customer needs it, we can manufacture hollow blades with Teflon coating. The rotating blades can be equipped with active protection welded on the blade, or we can use passive safeguards. It's like a flap on your baseball cap that prevents erosion happening on the blades. But of course, the flap is made of the same material. But basically, the flap takes on the erosion and protects the blade behind it, so it prolongs the life cycle of the blade itself. So that's the end of my presentation. Thank you. And if you have any questions, I'll be happy to answer. Thank you too. And before we have any questions from the audience, I would have a question, if I may. I noticed that on the last line, on one of the slides, there's a turbine which is running at half speed. So, well, if the market demands it, we're able to manufacture and install the half-speed turbine, but we don't have that demand. Dukovany? Well, we are rather ready to use a full-speed turbine to go in that direction. Well, okay, do we have more questions? I first of all wanted to thank you for your interesting presentation. Hopefully everybody liked it, but I have a question, or extend the previous question. Well, during Nuclear Days, we have seen presentations of potential suppliers of new units to the existing NPPs in the Czech Republic. And for example, there was a Korean company that presented, and I should know it, but I probably have forgotten. So I wanted to ask, a Korean company, Doosan, they also manufacture steam turbines. Do they have a half-speed turbine or not? Well, I must admit, I don't know. Well, I can give you an answer. Yes, they have it. Well, then it's a handicap, isn't it? But if I make it more complex, they have a half speed of 1800. That's their half speed. Okay, that's all I wanted to know. Okay, we're waiting for a new nuclear unit to be manufactured, so hopefully we will have more and more such exchanges of information and data. So this is your honey from our bees, and the last presentation will be of Mr. Neumann. heat accumulation to increase NP flexibility.
Hello, everyone. It is a pleasure that I can give my presentation here today. You can see the topic of the presentation, and I'm not only going to talk about turbines with heat extraction, but also about heat accumulation that could increase the flexibility of the nuclear power plant. The situation on the energy market has changed, and it keeps changing, and the standard coal power plants, which offered extra services and ensured the balance of the entire energy system, will no longer be here. Therefore, we should utilize nuclear power plants more than we have so far. You can also see notes that I'm not a technologist and I'm not primarily a nuclear specialist. I'm a cybernetic specialist, as you will see already in the first part of the presentation. In terms of climate goals and NPPs, I was encouraged by taxonomy that was approved this year. So I remind you in my presentation of advantages of utilizing NPPs. The first advantage is that NPPs will replace coal power plants. So we will reduce carbon emissions and we will reach the desired carbon neutrality. And the second advantage could be higher flexibility of NPPs thanks to two possible uses, not only the electricity production, but also heat extraction. And at a constant power output, we can also change the electricity power output by extracting heat. And then NPPs are good for increased stability of the entire grid system, and they can remove the breathing effect, the inertia, and they can lead to inertia of the entire grid system. In most cases, nuclear power plants operate in the load follow mode, which means the base load. Of course, that we can also operate in the extended load follow mode, which is more flexible, and it is often used in French NPPs. The French NPPs can several times per day run in a power output range from 1 to 100%, from 20 to 100%. We've never seen this in our context. And even the secondary regulation, which was certified in the past, is no longer used, and it hadn't been recertified because we hadn't really used it, and it was a lost investment. And to the advantages, I added the heat follow mode. That is my idea. This mode means that we follow the load by the heat extraction, and based on the heat extraction, we change the electricity load. So whether we produce more or less electricity doesn't really matter, because the entire system will balance it out somewhere else. But the grid systems are small, So meeting the extraction diagram is essential. I mention here Dukovany and Brno, which was an intended project. It is still intended. It's been like that for 30 or 40 years. In the past, it wasn't very economically viable because we had coal and it didn't make sense to use long distance heat extraction. But things have changed, and projects that used to be or were not economically viable and also were not feasible in terms of energy efficiency and were considered low efficiency project, because we were taught that electricity is the most noble, the best form of energy. So it is a blasphemy to make another energy out of electricity, but this is no longer true and this is no longer valid, and we have to adapt to this. So the way we use sources and the way we see them has to take this into account. So despite economical predictions, this will not work out if we take those into account, because there is a question of financial models and debt, etc., and that prevents new builds to be constructed. So in these terms, nuclear energy is not really favorable. And now let's look at the different modes and configurations. This is the case of the basic mode. You can see that the reactor runs at a stable power output, and there are only slight changes in output because the turbine makes up for the breathing of the system. This is the opposite mode, the load follow mode. Here, the output is regulated from the power of the turbine. Turbine reduces and ensures the inertia, so it responds to the orders of the dispatchers of the grid system. And this is the heat follow version. It looks like this. As you can see, we measure the heat extraction, so the reactor is regulated from the turbine mostly, but the grid system deals with the dispatchers' orders as well as the orders from the heat plant dispatchers. And this part is about turbines for district heating from reactors with saturated steam, and possible configuration of the plant hall. The type corresponds with a power plant such as Temelín, about 1,000 megawatts of power. You can see that there are several examples of heat extraction from 116 megawatt to 2,320 megawatt of heat.
So I put the data into a table, which in its scope corresponds to the table presented by my fourth speaker, but it is not so comprehensible in this case. It would be easier to follow the previous parts of my presentation if you could have this table in front of your eyes all the time. But what I'm trying to show is that on each line I have different configurations, lines A to F, and the columns are the different consumption regimes from 116 megawatt to 2320 megawatt. So try to keep this table in your memory. So on line A, we had steam extraction from NT turbine, from the low pressure turbine. And if we should use the heat for heating in a relatively small volume, then the best case is to use a non-regulated consumption in a low pressure section. That relates both to case 1, 116 megawatt, and also case 2, 348 megawatt. But the question is whether in a non-regulated extraction, the higher volume would be economical. But for small extractions, the non-regulating scheme should be enough. It has its advantages because you can use simple structure and you don't need to have any superstructured devices if you compare it to standard solutions. Line B, that is a separate standalone heat turbine on the main shaft, but you need a structural modification of that turbine, and it is better to have that heating turbine on one shaft with the low pressure part. It's image 1, line B, column 1, line B. So for all 4 modes of extraction, we have line B with standalone heat turbine on the main shaft. So when I look at the 116 megawatt extraction, the one flow, single flow turbine, heat turbine is counter pressure. Then B2, line B, column 2, that's extraction 348 megawatt. You need to have a dual flow asymmetrical heat turbine with counter pressure. And 1160 megawatt, it would seem that a similar alternative as in 348 megawatt is suitable, but it would be probably best to make the turbine smaller from 3 units to 2 units. So you should have 2 units, 4 flows. Then line C, that is a standalone heat turbine with its own generator. So if you use that device only to generate electricity, then the cooling steam for the heat turbine to support condensation is not necessary. So you can take the whole heating turbine, and put it off operation. It has its pluses and minuses. I will not get into further details. Let's get to line D, which is a low pressure turbine with its own generator. If it's located on a standalone shaft, then you can turn it off without the loss of cooling steam if you, for example, only heat during winter. So line D and line E as well is fit for very large extractions. And line F, that is an autonomous heating or heat turbine, and you can completely isolate it and extract steam, live steam beyond the reactor or steam generator. It is suitable for all volumes of extraction. Again, it has its pluses and minuses. So this is a brief specification by level of extraction from the smallest to the largest. So this brings me to the part when I'm saying that accumulation can help flexibility. It can increase flexibility. So the table, that large table, still applies, and now we can combine it with accumulation that further increases flexibility. So the column on the left-hand side, nuclear power plant with heat extraction, with peak turbine, the SEAT, plus potentially it can have accumulation as well. In the other columns, I've got schemes and literature and description, brief description, and features. So you can see, for example, in the scheme, the second column, I'm referring to some images. I used background documentation, which is rather old, because, as I said, we gave priority to other setups because we had enough coal. So for a number of decades, nobody focused on this. So I have images, image 1, image 2, from documents that I used to prepare this presentation. On the last 2 lines, there are 2 images highlighted in violet, pink, whatever. And these are images of Mr. Drahi, and senior employees of Škoda will remember him, and younger guys in Škoda will probably remember his name from documents that they study from. And as for accumulation, I used materials produced by Professor Kadanoška. So in Prague, people from Prague know the Prague University world. So in Prague, we had Mr. Ambrož, who was an expert on turbines. In Brno, we had Professor Kadanoška as an expert on turbines. And you know who's the expert, or who was the expert in Pilsen. So the upper part is by Mr. Kadanoška. So I'll rather skip to the drawings. This is a nuclear unit with added heat accumulation in feed water, and it uses a direct pressure accumulator. And you can see charging and discharging on that drawing by different arrows, and that scheme allows us to switch among different levels of heat and electrical output. So I tried to include this in that large systemic table. So this corresponds to line C, column 3 in that heat table. And it has a peak turbine shot plus accumulation plus 3 steam expanders. So again, that changes the layout and setup, and it also changes the scope and speed of flexibility. So this corresponds to line C, column 3, C3. And the difference is that it delivers heat to a system. Well, the previous one also delivered heat to some kind of a system, but this one is used in peaks. And there are expanders as well. So it's a slightly different setup, a different solution. So this is a different setup as well. So the peak turbine would only be of a condenser type. So that corresponds to the previous scheme. plus the peak turbine included in the setup as it is, as you can see it. So this is for VVER 440 reactor turbine with accumulation of heat in feed water, then direct pressure or single pressure accumulator, and heat extraction into the heat system, heat distribution system. So now we're getting to the part that is originally by Professor Drahi, who's also an expert on peak turbines. And there are two alternatives. Either we extract steam for heat generation from the satellite turbine, which is installed in parallel to the main turbine. So that corresponds to line 3 or 4. No, 3/4. So line 3, column 4 on the image 2. So 1500 megawatts. And the second alternative is that it's a satellite counter pressure turbine with its own heaters. So this is the first option. And I did not include all the details on that drawing, but basically you can either use a heater or you can extract live steam from the LP part, and I added those connections that were missing in the original schema. And you can also see the difference when you look at this one and the other chart. In the first setup, you extract heat only from the peak turbine, DS, while here you extract heat from the peak turbine and the main turbine. So, accumulation, in my opinion, is a suitable source of peak energy, and it can be up to 100 or 350 megawatt. And annually, you can use it for 500,000 or even more hours annually. You can use the low pressure condenser turbines in peak times. If you install the accumulators, you can increase the output by 20 to 35% with the same output of the nuclear reactor. And heat accumulation makes it possible to cover almost all different loads of the electrical system. And thanks to that, if you use nuclear power plants, you can cover the peak and half peak demand. That's what gas power plants used to provide. So to conclude, points 11 to 15, as you can see, the references to publications. And as Mr. Benir informed us what he's planning for next time, maybe next time I could focus more on what's in the last lines, the last publications, because it reacts to the current situation. So SMRs will not help the Czech heat sector. That's the first title. Then tender for Dukovany and possibilities of nuclear power plants to provide more flexibility. And the third publication is about whether it's time for a transitional rehab for coal before we have, again, enough gas or nuclear. Thank you. Questions?
Any questions? Nobody? Thank you very much. Thank you for the honey. It will be enough for my grandsons.
So, ladies and gentlemen, I would like to say thank you to all the speakers, also to the chairman of this panel, of this session. Thanks to all those that stayed with us in the audience till the end. And I can only state that our two-day international conference fulfilled its goals and it has successfully come to its end. So once again, thank you, and I'll be looking forward to repeating this again next year, or maybe modifying the setup of the conference. We'll see. In the beginning of this year's conference, we had a record number of signed up participants. We also had a good participation yesterday evening at our social event, so thank you for that. Also, thanks to all the sponsors, those that supported us and made it possible for us to organize this event. It's a relatively large conference. It has become a large conference over the years, and of course it has corresponding costs. So once again, thank you. And unless there's anyone who would want to contribute to our final discussion, then let me officially close this year's conference. So once again, thanks to all the friends to steam turbines, those that stayed with us till the end. So thank you again.